Good morning, Professor Voliar. This is Naveen Nischal from India. Okay. Okay, thank you so much. Should I start my presentation? Yeah. I hope my screen is visible to everyone.
Yes, it's clear.
Audible. Yeah, so first of all, very good morning to you all. Thanks very much for introducing me. My name is Naveen Nissal. I am from Department of Physics, IIT Patna, India. I must thank Professor Boliar for giving me this opportunity to speak to you about my research work, which is very well matching with the theme of the conference, structuring the light, and how that light beam can be utilized for securing information or image or data. So the outline of my presentation is I shall talk about in brief about the optical crypto system, then in brief about the optical orbital angular momentum of light, optical singularity, then vortex beams, how they are generated and detected, and role of self-referenced interferometry in characterizing the vortex beams, and how these beams, these vortex vector beams, can be used for making a security system or for authentication applications. And with that, I shall conclude. So first is the structuring of the light. So that part first. So interesting property of light is that it can be shaped spatially or temporally. So what are the parameters which can be tailored? So those parameters are intensity distribution, wavefront, polarization. So these optical fields which are shaped or sculpted for a purpose are studied under the topic of the structured light. Now there are three important parts attached to that: how to generate such a structured light, how to measure them, and what are the properties. And of course, when we study all these, so what are the applications where we can utilize them? So how to generate? There are techniques based on diffractive optical elements, like based on diffraction properties. Then there are methods where we can use spatial light modulators to generate such beams. Next comes how to measure. So again, for measuring such beams, we have to use the interferometric technique, polarimetric technique, or diffractive methods. So those are the methods through which we can measure them. And the properties and applications, like we can manipulate, use in the optical manipulation, imaging, optical metrology, optical cryptography, quantum cryptography, and communication is a very big way where we can use these properties. So coming back to the polarization ellipse, that in the state of polarization at which spatial points in the transverse plane of optical field can be represented using polarization ellipse. So there are two parameters to be characterized, like they are the ellipticity angle and azimuth angle. So we have two states of polarization in a way that one is within we call it as the homogeneous polarization, or we call them as scalar beams. So in that case, the state of polarization is uniform. But in inhomogeneous polarization distributions, the state of polarization is not uniform. Such fields, we call them as the vector field and also the elliptic field. Now, this angular momentum of light, which is very important. So this is a vector quantity that expresses the amount of dynamical rotation present in electromagnetic field of the light. So there are two types of motion possible. One is the spinning, another one is the twisting. So when light wave is traveling approximately in a straight line, a beam of light can also be rotating, and that rotation is maybe in the form of a spin or the twisting around its own axis. So accordingly, we have two types of momenta: spinning angular momentum and the orbital angular momentum. So these two forms are they give rise to the spin angular momentum and the orbital angular momentum. This is what we can see them. So it is necessary to know that the total angular momentum of light and matter is conserved in time. So when a light beam is carrying non-zero angular momentum, it impinges on an absorbing particle. Its angular momentum can be transferred on the particle, thus setting it in the rotational motion. So this occurs both in case of spin angular momentum as well as in the orbital angular momentum. So if the particle is not at beam center, two angular momenta will give rise to two different kinds of rotation. Spin angular momentum will give rise to a rotation of the particle around its own center, that is a rotating spinning, and OAM, orbital angular momentum, will generate a revolution of particle around the beam axis. So this is what they happen in case of spin angular momentum, and this is the orbital angular momentum. So spin angular momentum is credited because of the state of polarization, and orbital angular momentum is because of the wavefront shaping. So in this case, it is important to note here what do we mean by the optical singularity. So parameters which describes an optical field are amplitude, phase, polarization, etc. In optics, this singularity refers to a point at which some parameters, which are describing the field, which become indeterminate. Now it can be, phase can be indeterminate or polarization can be indeterminate. Accordingly, we have phase singularity and polarization singularity. And around singularity, large gradients of the parameter circulates, which give rise to unique properties. And this is what we study under the topic called singular optics. So other than optics, singularity also occurs in many natural phenomena. So the types of optical singularity, depending upon if the phase is indeterminate, we call phase singularity. If polarization singularity. So optical fields with singularity have spatial inhomogeneity, and polarization singularity arises because of the vector nature of light. So this phase singularity, so this is what the expression through which we can refer the phase singularity. So at singular point, intensity is zero and phase is undefined. So optical field where singularity occurs is also referred to as optical vortex. This is what is important here, and we'll deal with that, such beams. In polarization singularity, a state of polarization at each spatial points in transverse plane of optical field can be represented using polarization ellipse. So polarization, to characterize polarization ellipse, are ellipticity angle and azimuth angle, as I told in the beginning. At the point of polarization singularity, ambiguity is in the azimuth angle. So vector fields can be represented by this expression. EXY is EXY prime vector E and EY. So these are the different fields, we can denote them. So light beams with singularity, we call them as the singular beams. So light beams embedded with optical singularity are referred to as singular beams. And commonly known singular beams are vector beams. So vector beams will have helical wavefront, phase singularity along the beam axis, and may be homogeneously polarized. But another types of singular beam, what we have is called vector vortex beam. They show vector nature of light. It is inhomogeneously polarized as compared to the vortex beam, and have both phase and polarization singularity. So such beams are more attractive for many reasons. So vector vortex beams have both phase singularity as well as the polarization singularity. So vector vortex beams, they can be described by the Lagrangian modes, which are the solution of the paraxial wave equation in cylindrical coordinates. We have these parameters phi, azimuth angle, and the topological charge and radial index. If you plot them, so why vortex beams are important? The importance lies that one of the main reasons of growing interest of the singular beams is their association with the orbital angular momentum of light, means they are associated to each other. In 1992, Allen and their colleagues they showed that a vortex beam which have azimuthal phase dependence carries orbital angular momentum of LH cat by 2 pi per photon, where phi is the azimuthal angle and L denotes the topological charge. So in comparison to the polarization, orbital angular momentum have larger number of orthogonal modes. And this is since it has larger number of orthogonal modes, this is the important feature which attracts people working in the area of optical communication, quantum optics, optical and quantum cryptography. We exploit those features for those applications. Other applications are in optical trapping, optical metrology and optical imaging. And optical trapping, this optical tweezer application is very well known. So vortices are ubiquitous in nature. It ranges from spiral galaxies to the Milky Way to dynamic ocean circulation and even to Bose-Einstein condensate. Optical vortex in a structured electromagnetic field has a helical phase singularity that possesses photonic topological charges. Such a singularity in light is closely linked with the angular momentum of equivalent. Orbital angular momentum could provide an additional degree of freedom for data multiplexing, and that is why we have more interest in the optical communication area, whether it is free space communication or in communication through fiber cables. Vortex beam to be used as tweezers to assemble DNA biomolecules, super diffraction limit imaging. This is what the optical imaging we have been saying. This is where the optical vortex has the utility. This is well-known figure from the topological charge of the vortex beam. So I will skip there because this is known to everyone. So how we apply this concept in optical security? This is our important aspect. But before that, how to generate such beams? So generation of vortex beams, and of course for generation, liquid crystal based spatial light modulator is a very handy tool. And this, particularly the Pluto SLM, which has the phase characterization up from 0 to 2 pi, is most important tool. So phase modulation in light can be introduced by the SLM, which can be controlled through a computer-generated hologram. So you can fabricate a computer-generated hologram. You can synthesize that in your computer and display it on the SLM, and you can generate the vortex beams. Then comes how to detect and characterize them. So detection is the diffraction-based methods. You have to have an unknown vortex beam that is meant to pass through specially designed phase masks, and resulting diffraction pattern is analyzed, and this is what it gives you the topological charge, means the value of L. Recently also there are many techniques which are being reported based on the diffraction. Another technique is interference-based method. So in interference-based method, you have the unknown vortex beam, and that is meant to interfere with a reference beam, and resulting fringe pattern is analyzed. So you have to have two beams. One is the unknown vortex beam, and it is going to interfere with a reference beam. And once we get the interference pattern, then we analyze the interference pattern, and through that fringe pattern analysis, we come to know what is the topological charge, or what is the L value. So it requires a simpler analysis and more intuitive than the diffraction-based methods. But recently, some of the researchers have also claimed that diffraction-based methods are also good. Both the methods are used. In both the cases, you have to, in diffraction case, you have to look at the diffraction pattern and analyze, and from there you conclude what is the L value, the topological charge, and same thing in interference case also, you have to look at the interference pattern, and then we measure what is the topological charge. So one of the patterns what I am showing you here, it is based on the interference of vortex beams with the reference beam. So you have the beam 1 and we have the beam 2, and we have this interferogram. So similarly here, beam 1, beam 2, we have the interferogram, beam 1, beam 3, 2. There are three cases. So So here you have to count the number of times, and accordingly we denote what is the vortex number there. Another geometry based on this interferometry is on self-referenced interferometric methods. Now this is a bit better method, I should say, where you don't need a separate reference beam. Instead, the object beam itself works as a reference beam, and that is why we call this as the self-referenced interferometric method. So no additional reference beam is required here. So our experimental setup becomes easier. A known vortex beam is meant to interfere with its own amplitude spectrum. So you have the only unknown vortex beam, and that beam is interfering with its own copy. Interferometric setups are especially designed to produce well-defined fringe patterns, and it allows the measurement of both sign and magnitude of L's. So it is plus L or minus L, both can be measured. It can be also used to measure the topological charge of vector vortex beams. So how this self-referenced interferometric methods work? This is the interference using a laterally displaced replicated beam here you can see. So we are introducing some tilt, in this case with tilt along the direction of displacement. Second case with tilt orthogonal to the direction of displacement. Third case with difference in curvature. All are self-referenced method. Second one is you can have it in the inline interference method or off-axis interference. All are possible here. In all the cases, we can state the sign and charge of the topological charge of the beam. Interference of vortex beam with its displaced replicated beam. This is another geometry where the beam has been displaced replicated beam. So same copy, but the copy of the original beam, but it is displaced. So we introduce some displacement, maybe delta x and delta y displacement along x and y directions. So this is the tilt function what we have. So in this case, how the symmetric diagram is shown here to obtain the interference of vortex beam with its displaced replicated beam. As you can see in the tilt, we have introduced this delta x component, delta x and delta y component here. Delta y here has been introduced. So you have displaced the beam by the amount of delta y. And again, doing everything, it becomes easier when you deal with carry out this experiment with the spatial light modulator, SLM, which is computer controlled. So these are the results of the displaced replicated beam we have introduced, and this is how we can measure what is the value of the topological charge. L is basically n-1, so count the number of times a fork-shaped structure, how many of them there, and -1 will be the topological charge. Details you can see in this paper. So interference of the vortex beam with its conjugate replicated beam. This was another AB extended area where instead of that replicated beam, we can use the conjugate of the replicated beam and again carry out the whole experiment and see the result. For doing this, achieving this geometry, this effect, we had to use a prism. Now here the prism has been used not to introduce the dispersion, but rather only it has been in such a way that it introduces the conjugate, introduces some displacement, a replicated beam, and you are introducing that displacement here. That delta y thing, what you can see here. This is the geometry where this M1 plays a very important role here, through which you can displace. And these are the results based on that pattern where you are using the conjugate replicated beam. So more details you can look at this paper with Josai and see these things. Now when we have done this generation of vector beams, so as we know that the vector beams with spatially variant state of polarization, phase plays a very important role in spatiotemporal evolution of an optical field. You can have the simultaneous manipulation of both polarization as well as the phase of the optical field. So the challenge is tailoring the phase of vector beams due to lack of a reliable way to modulate phase of a vector beam while leaving its SOP intact. This was the main challenge. So for that, and this we wanted to utilize it for the security applications. So what we did, we have this laser beam. This was all simulation based, You have to use a quarter wave plate and you can play with the different orders. So what we did, this was the algorithm for the security application. So Stokes polarimetry of the spatially variant polarized beam. So you have the spatially variant state of polarization that can be used as the encryption keys. So spatially variant state of polarization, we are using it as the keys, security encryption keys. And in this case, we applied this Gertzberg-Saxton algorithm to evaluate the phase only function of the plain text. So you have some information that has to be encoded. So we calculated the phase only function through this GS algorithm and then generate the vector beam with that phase. So a Stokes parameter of the beam is recorded, which serves as the ciphertext and key. This what the algorithm is. So how the phase tailoring of the vector beam is done is what the basic principle. You have the transmittance of a grating, that equation can be expanded, and you have the optical field at back focal plane, Fourier transform plane. So we used a spatial filter to filter the first diffraction order along X and along Y axis. And selected beam is converted to left and right circularly polarized light using a quarter wave plate. So using that quarter wave plate, select the order, filter them, and then we can apply LCP and CP through the quarter wave plate, λ/4 wave plate. So selected beams are allowed to pass through a lens and hence they are recombined. This is what we get. So omitting the constant amplitude factor after doing all these modulations. So this will depict you the spatially variant state of polarization. So measure the Stokes parameters S1 and S2, and this what the values will be. So once we have noted those values, this is actually how the experimentally one can record. We have done the simulation, the experimental part is still to be done. We have done some additional study in this case, and show you at the end. So here, these are the two fields here, and we are using two quarter wave plates, considering two diffraction orders, and introducing them and calculating those parameters. And from those, with the help of those two Stokes parameters, you can decrypt the whole information and get the decrypted original information back. Of course, you have to use the same keys, what we have produced during the process of encryption. And the GS algorithm is there to produce that phase only function. More details are there in this paper. These are the simulation results, like this, the input image. So you have these two phase only functions, phi1 and phi2, and this shows the polarization state distribution. These are the two Stokes parameters, and this was the key. And once you apply them in the correct order, the same information, we are able to decode the original information back. So this is where the concept of this such beams have been introduced for security purpose. So this is the input image, second input image. So instead of one, we can apply extend this idea for multiple image encryption. This is what the concept is. Again, we can use it for the authentication purposes also. So where if the two information are matched, you get the correlation P. Otherwise, you don't get a correlation P like this. For that purpose, you have to separate them into true class image and false class images, and corresponding the phase only functions. Here we have further modified that Gertzberg-Saxton algorithm, and this one called as the MGSA, modified GS algorithm, and we carried out all the experiments, and then we come up with the idea, and it works very well for the authentication purpose. So this concept not only for securing a single image, securing multiple images, and further for authentication applications, everything we have carried out, and this is what the result is. Further, since this the vector beam what we had generated in those simulation study, that are known fields. So there was a chance that somebody can duplicate that vector beam. So can we generate arbitrary vector beam encoding? And in that case, in the previously case, we had to modulate both X and Y component. Can we modulate a single component and use it for the security application? Then what happens in that case? It becomes more stronger. The security will be higher in this case when you are dealing with the arbitrary vector beam, and instead of modulating both, we are doing the single modulation. This is what we achieved in this case here. So you have, suppose these are the plain text, again applying that GS algorithm, and we have this is the proposed encoding scheme. You are encoding in the one dimension only, in one modulation only, single modulation only. That's how we can write the encoding optical field. So this ciphertext in this case is obtained by recording the Stokes parameters of the optical beam and using the following relation. This is the relationship for the S0, S1 parameters. Key is defined in this way here. Decoding a scheme is just reverse of that, but of course with the correct keys what we have applied during the process of encryption, we have to apply them in the serial order, then we can decode it correctly. So we can decode one by one all the information. One image, one data, then second image, or second data, third image, and so on, so forth. This can be also done for not only black and white image, it can be used for the gray level image, it can be used for the colored image as well. So while implementing this optically, we used a QR code concept also, and QR code is a very noise tolerant, it is binary. So we applied that concept and combined that with here. So these are the plain text 1, 2, 3. These are the retrieved information 1, 2, 3. You can see this is the simple experimental setup. Again here the SLM becomes a handy tool which helps you to modulate the single component and achieve that. So these are the results based on this arbitrary vector beam. This has been recently published in this IEEE Photonics Technology Letters. You can see more details in this paper here. So I think I am coming to an end of my talk. So to conclude, I discussed about the self-referenced interferometry scheme to determine the topological charge of unknown vortex beams. I must iterate here that many researchers have claimed that diffraction-based schemes are better. I cannot counter that which one is better, but what we have worked on this interference-based techniques and found it useful, found it good. So different configurations of self-referenced interferometry, like one is the lateral interferometry, simpler to implement and can be used for topological charge measurement in an unambiguous way. Methods based on interference with a conjugate replicated beam, which was used to determine the topological charge of high order vortex beam, even if they have non-zero radial indices. Demonstration of the vector beam based crypto system is what I did, one for the general vector beam and another one for the arbitrary vector beam. So thank you very much. I must acknowledge my students whose work I am basically presenting here. And on this topic of this cryptography, I have recently written a book, which is also published from IOP. If somebody is interested, you can write to me. I can share a soft copy of this book with you. So the title is The Optical Crypto Systems. So it was published in December 2019. So a hard book, hard copy, as well as the ebook, both are available. So thanks very much for your kind attention. Thank you.
Thank you, Professor Nishal, for the brilliant talk. And now we have time at least to one questions. We have auditory here, and if the question will be, we will translate it and print it into the chat. Maybe I have a short question. Do you presented a brilliant results about crypto systems with polarization in homogeneous radiation? Do I correctly understand that it is possible to extend the common optical encryption system like a double random phase encoding system and in Fresnel zone with your polarization state techniques? How it's related with the standard scalar encryption systems?
Yeah, very good question. Of course, we can extend it. In all the encryption systems, optical encryption systems, the basic idea come from double random phase encoding only. So here also you do the encoding. Now, in many cases, it is not necessary to do the double random encoding, and many cases you can go for more than 2 encoding. So instead of random phase pass, we can create vector beam or different beams concept here. And of course, you can do it for the Fourier domain, Fresnel domain, fractal Fourier domain. Everything is possible. And so there are many reports where such things have been reported. So state of polarization based, again, it is very handy. And here it is important to note that I did not tell you that part, that having based on the polarization concept, it is easy for a practical optical crypto system, because polarization you can record it becomes intensity based. So even if you have the encrypted data, it is in the form of an intensity, not as a complex function. So then storage transmission becomes easier. So that's the additional benefit what such systems have.
Okay, thank you. I think we need to move to the next talk. We would like to thank the speaker again. And the next talk is Professor Keha Singh. It's plenary talk. The title is Optical Cryptography, a Personal Tour. The result from the beginning of this 21st century. Professor Keha Singh, are you hear us?
Mr. Chairman, give me a few minutes, please.
Okay.
На самом деле, интерферометрию мы публиковали 4 года назад, но задавать ему вопрос, читает ли он наши статьи, я ему не стал. В смысле. Буквально картинки те же самые. И для нас еще другие люди печатали из Англии, у нас немножко разная схема интерферометра. Дурная манера не читать.
Может, как раз читал.
Может, читал, да.
Давай, плати, я поеду. Оплачу твою, твоего автомобиля. Ну, только нет. А он не Давай, понимаешь, говорить об одном и том же, только разные детали. Вот эта передача ключа у нас, по сути дела, является применение опорного источника. Вот у нас есть патент, значит, как такой, называется бесшумовая система передачи информации. Значит, там как мы передаем чистым полом.
We
Mr.
ready?
Chairman, I'm ready.
Yeah, thank you. You can start, please.
Do you see the screen?
Yeah, we see the screen, we see you, so you can start.
Thank you, and sorry for the delay. Thank you, Mr. Chairman. May I say how happy I am to be a part of this conference. And I thank Professor Goliar for making this possible. So welcome to my presentation, which is on optical cryptography. It's a very brief account of my personal tour, which started in 1998 or so, and it still continues. It will be foolhardy for me to go into the details, so I'll restrict myself to some very sketchy glimpses only. Particularly optical information processing. Optical cryptography is just a small part of larger area of optical information processing. So we were working with the photorefractives, particularly photorefractive crystals, and performing experiments on 2 and 4-way mixing, self-diffraction, multigratings, optical image amplification, image processing, laser speckles, dynamic holography using these crystals, digital holography, optical correlators, and their applications in image processing, pattern recognition, and metrology. So that was IIT Delhi, and then at another university in Gurugram, very near to Delhi, I have this group consisting of 4 faculty members and some students. And the work here has been reported in one of the books, so one can see these for details. Also, for those who are very much interested in this topic, I'll recommend these 2 articles by me. One was published in 2016, and this describes our work until 2015 or so, and that mainly made use of canonical transform, double random system and its various modifications that Professor Naveen Nishchal talked about briefly. And the second one was on the speckle coding for optical and digital security applications. So there are various definitions of encryption, and of course in digital processing a lot of work has been done on this. So digital encryption preceded optical encryption. In very short, I can say that we want to jumble up the information in such a way that it becomes inaccessible to the unauthorized users. Now, there are various optical routes open now for authentication, watermarking, and image hiding, and progress on daily basis continues to be made. There are 2 main types, symmetric and asymmetric systems in digital processing of digital encryption. These have been known by the names of private key and public key. But for enhanced security, one has to introduce many modifications, including introducing nonlinearities and many other methods. So this is a brief outline. I've already talked about information optics, particularly the part that we are involved in. We also worked on holographic storage and made these holographic memories secure, but I'll not talk much about it today. Advantages of optical processing over optical cryptography for the digital cryptography are now well known, and Dr. Naveen Nishchal also pointed that out. So I'll start with double random phase encoding, then go to Fourier transform and fraction Fourier transforms and some other integrals, particularly fraction Mellin, gyrator, fractional Hartley, and the use of ideas from the singular optics. Using Devil's vortex Fresnel lens, and which is a diffractive optical array. In fact, here I must point it out that Professor Khorina and Professor Kocheliar and their group in 1992, Journal of Modern Optics published a paper by the title "The Rotor Phase Filter," and in literature it has also come to be known as radial Hilbert transform. So both the names are currently in use. We also worked on Arnold transform and single value decomposition, but I think I like to concentrate on the structured phase masks and their use in singular optics, because singular optics is the theme of this 10th conference. And various types of attacks have been carried out and countermeasures given, and then I'll sign off with some concluding remarks. So in this age, which is characterized by a lot of generation of transmission, detection, processing and storage of retrieval, the importance of security is very important, is very obvious, and the application areas are many, including communication, defense, multimedia, e-commerce, computer network, medical record, intellectual property, copyrights, and several others. And for holographic videos in memories, optical route seems to be the only method for making these see join. As I said, I'll not talk about holographic memories, except to point out that two of these students, Renu John and Bhargav Das, obtained their PhD degrees in 2006 and 2010. They worked extensively on image-based methods, developed some modulation codes and some security aspects, which was important for today's talk. Gave various defocus techniques, gray level phase modulation, and worked out the bit error gate characteristics. Now obviously, optics had advantages over the counterpart in electronics, because by the very nature of optical processing, it's a parallel processing. Fortunately, the enabling technologies of optical fiber communication, precise optical components, CCDs, SLMs, and holographic discs, etc., and also the newer materials, photopolymers and photoreflective, have given fillip to the subject. In future, using photonic integrated circuits, miniaturization is possible. You can use beta materials for writing holograms, or for that matter, any optical components, which should lead to miniaturization of the equipment which is not so far commercially available. Now, the advantage of in fact, this graph shows my private collection, but I might have missed many of the publications. And you can see that starting with only one paper and one conference report in 1995, there has been very feverish activities, and there has been almost a there has been very rapid growth until 2021, up to 2019. And a lot of literature is available these days. There was a book by Al-Falau, published in 2018, and of course Naveen Nishchal published his book, Optical Cryptography, which I have just shown. And there are a large number of special issues of various journals and detailed review articles, advanced optics and photonics. This is a very valuable list of resources. So let me come to the topic proper. The whole thing started in 1995 by this paper of Refragier and Javidi, published in Optics Letters. It's based on a double random phase encoding method which makes use of the 4F system. So you start with the image that is to be encrypted, bonded with a random phase mask, and do a Fourier transformation by the lens. It is shown here. You have the Fourier transform in the back focal plane where you keep a random mask by number 2. It should be remembered that the two phase masks are independent of each other. Then you do another Fourier transformation and you get the encrypted image, which is a perfect noise. For decryption, you go in the reverse fashion. This method is very simple, of course, and it held the field for about 5 years until in 2000 it was attacked, successfully attacked. And it was shown that the method is susceptible to known plain text and chosen plain text attacks. Now, as I said earlier, we were working on phase conjugation using photoreflective crystals. After probably 1.5 years of publication of this paper. In Applied Optics 1998, we published our results on optical encryption system that uses a phase conjugation with the photoreflective crystals. Come in a moment to this. Then we did the fractional Fourier transform instead of full Fourier transform, and enhance the security. Because now an additional degree of freedom is available to us. And fortunately for us, as on September 5, 2021, there are about 1125 citations on Google Scholar, though I know from my personal collection that the number is close to 1,400, because some of these have not been reported in Google Scholar. So we continued with these investigations, and using fractional Fourier domain, we encrypted holographic memories by using anamorphic optical systems and reported our results in 2001. So I'll take just one of the examples. This one, of course, full Fourier transform. So you start with the image, bond it with the phase mask, do a Fourier transformation. In the Fourier transform domain, you have a Fourier transform of the multiplication of fx and rx. That means the object and the domain. But instead of using the conjugate phase mask, as is the as was the convention in the process of decryption, we worked with photoreflective crystals. So the signal and a reference beam wrote a volume hologram in a photoreflective crystal. It was lithium niobate at that time. No, I'm sorry, it was barium titanate at that time. And then there was a readout beam which is contradirectional to the reference beam, generating a phase conjugate wave propagating in the direction opposite to that of the signal. So this obviated the necessity of using the random phase mask conjugate of the random phase mask 2, which was in the Fourier transform. Because there are difficulties with the vibration, which I cannot go into at this stage. So this is the experimental result. You start with the original signal. These were actually transparencies at the time, and you get the encrypted image, which does not resemble the actual image at all. And you have the decrypted image and the decrypted image with the wrong encryption key, wrong decryption. These are not very good results. But later on we got the results. So this is how fraction Fourier transform is defined, but I will avoid the mathematics. So Unnikrishnan got his PhD degree in 2002 by using fractional Fourier transform domain, encrypted holography memory, polarization encoding, and coordinating phase systems. Then Naveen Nishchal continued the investigations and did work on digital holography, full phase encryption, some other methods using cascaded and localized fraction Fourier transform, and some other modifications. Then we continued, and in 2009, Anit Naledi got his degree by working on three-dimensional object reconstruction in information security using digital holography. So this is the paper from Naveen Nishchal in 2004. There are certain advantages in using a fully phased encryption. That means instead of working with the intensity objects, we convert these into phase objects. And these are less susceptible to noise. That was known at that time. We have shown for this case also. So you put the amplitude image on a phase only SLM, and that is the object beam, and then you have a reference beam in which there was a random phase mask, and you record a hologram. So that is the encrypted hologram. Then you generate a key hologram, you get the encrypted image and the decrypted image. Of course, you cannot see this because this is a phase image. So you have to go through an additional step of converting the phase image back into the amplitude of the test image, which can be done using a photoeffective crystal or by interferometric methods. So I'll avoid the details. Madhusudan Joshi continued investigations on this by working on color and grayscale images in the Fourier and fractional Fourier transform domain. And then we introduced this concept of radial Hilbert transform filter, which I said earlier is actually the phase rotor filter described by 29 others in 1992. And we tried to make the method nonlinear between the investigations. Then Madan Singh worked on cryptographic methods using laser specking, various methods. So the review article that I had shown you earlier was actually an outcome of this dissertation. And then work was continued by Pramod Kumar, who used modified Lohmann system for giving new methods and using holography. He worked on silhouette removal, and he also worked on attacks, particularly point spread function attack and countermeasures. So I'll avoid the details regarding holographic memory encryption and go to one glimpse of a holographic cryptography using Fresnel domain and convergent random illumination. You have two lenses whose functions are randomized by using two random masks, which is made by using coated gelatin. And then you have one object beam and one reference beam, and recording a hologram on the photoeffective material. This was Fresnel geometry, so you could vary the object distance or the reference distance, which is convenient. This is the experimental setup. These are the experimental results. A is the original image, B is the encrypted image, C is the encrypted image reference beam, D is the decrypted image with all the correct parameters. And then if you have deviations from the distance of convergence, then you progressively get an image which is almost absent. In addition to Fourier and Fresnel transform, we work with gyrator transforms, with Hartley transforms, with Hilbert transforms, Mellin transforms, and their fractionalization. So fortunately, for quite a few of these, optical fractionalization of full transforms is possible. But the sensitivity, but the security of the method should always be tested on a very, very old principle which was given in the context of digital encryption, which says that the security must reside entirely in the keys. So if an attacker has complete descriptive knowledge of the cryptographic algorithms and implementation, he should not be able to attack the system. And there are various kinds of attacks, like brute force attack, chosen cipher text attack, chosen plain text attack, known plain text attack. There was a review article published in 2015 which gives information about quite a few of these. And now I come to the use of singular optics in recent investigations. So in an investigation using fractional Mellin transform, you have to use the technique of phase retrieval. We use structured phase masks, and particularly Devil's vortex phase structure, which I'll come to in a moment. Also, in image watermarking, we use the gyrator domain. We worked in the gyrator domain and used the Devil's vortex Fresnel lens, and so on. We also used the fractional Hartley transform, Arnold transform, and singular value decomposition. We worked on color objects also. In our latest, in 2021, is a paper on security analysis and modified attack algorithms for a non-linear optical crypto system based on double random phase encryption. There are several review articles. So let me come to the Devil lens based phase function. It's given by the mathematics here. It's described by a one-dimensional Cantor function. Mathematics is given here. I'll not try to read it out. So for certain value of this Cantor set, S, which is denoted by S, and value 2, the staircase looks like this, can be changed by changing the value of S. And you can generate it for various values. So in this case, you start with a rectal zone plate. Here I have shown it only for S is equal to 2 on the left hand side, or S is equal to 3 on the right hand side. So let's concentrate only on the left hand portion. You combine it with a phase rotor, radial Hilbert transform. I have it in A plus B, A plus C, because I'm saying that I'm combining it with the phase filter. In optical implementation, of course, the two phases get multiplied. And you come out with D, which is the multiplication of these two parts. Then zone plate and the rotor filter. And the DVFL, which in our case is a phase key, is this C, which means obtained from A, C, and D. So these are the mathematical expressions for the radial Hilbert transform, for the lens function, for the phase mask. This is of course for vortex phase lens, multiplication of the three phase functions. Then we worked in the gyrator transform, which is a modified form of the fractional Fourier transform, but it's easy to implement by using a three-lens system. And by rotating these three lenses, you can get a parameter which becomes one of the security parameters. So we start with an intensity object, convert this into a phase object, multiplied by a random phase mask, and also by a Devil's lens. Then then perform a gyrator transform of order alpha, then multiplied by another statistically independent random phase mask 2, multiplied by DVFL, where S is equal to 3, and then multiply by gyrator transform of order minus beta, you get the encrypted image. If you go in the reverse fashion, you get the decrypted image, which is shown by IXY. So you can see that there are a large number of degrees of freedoms available to you now. And these are some of the results. You start with input image, then DFL for S is equal to 3 is shown here. This is phase key. For S is equal to 3, phase key 2, and then you get the encrypted image. DVFL for S is equal to 2 shown on the right hand side, and there are various parameters because of the lens function, wavelength 632.8 nanometers, focal length 250 millimeters, and rotor filter parameter being E is equal to 5. Random phase mask, and then the reflected image. We did a correlation analysis to show that secure. Well, these are some of the sensitivity results where we have shown the results for incorrect value of the focal length of the lens, incorrect value of the wavelength, incorrect value of the rotational parameters, doing the gyrator transform, deviation from the phase value, and so on. Then a detailed security analysis, occlusion results, then fractional halt rate transform. Mathematical expressions are shown here. The Arnold transform, which is basically a scrambling operation, which changes the pixel position randomly. Then a singular value decomposition, which is kind of robust method for matrix decomposition. I'm not going to mathematics details. So shown here is the Arnold transform, original image for a certain parameter on the left hand side, and then for another value of the parameter. So you start with an object, turn it into a phase object multiplied by the random Arnold random amplitude mask, then do a fractional Hartley transform, then Arnold transform, similar value decomposition, and you get three functions u, a, and b. Then the decryption goes just in the reverse fashion. Then validation of the scheme is shown here. A is the input gray image, then BCD are the encrypted images for U, A, and B after singular value decomposition, and then the recovered image is E. F is with incorrect orders of magnitude multiplication in decryption, and these are the 3D plots showing the changes. Sensitivity plots related to the Arnold transform, which is the additional parameter available now. Sensitivity plots analysis for fraction Hartley transform, is also an additional transform, and then the results for decryption. Also shown are the two curves for effect of the noise. And this was our method which we described in 2021. So there was a paper in optics and laser engineering in 2020, which went like this: that you have an original image multiplied by one encryption key in a non-linear term, do a Fourier transformation, multiply by another encryption key, do a reverse Fourier transform, you get the encrypted image. And then in Fourier transform, encrypted image gives you a parameter, gives you an image function, multiplied by decryption key and inverse Fourier transform gives you the decrypted image. So they implemented by using the well-known core system, but this is the time-varying parameter shown in the lower part of the slide on the left-hand side. So A is the input image, B is the random phase mask 1, C is the nonlinear term, D is the random phase mask 2, and you get the encrypted image. Now decryption can be done and final decrypted image can be obtained. But the method was susceptible to the conventional known plain text attack. So we gave our method which obtains a decrypted image which is not susceptible to the conventional image. So you have the random phase mask. You start with the random phase for initialization, IP, and go through these various stages of Fourier transformation, multiplying by a function, then another stage, then FD star, inverse Fourier transform, and then generating this correlation factor. And if it is satisfactory, then you stop. If not, you apply certain Fourier constraints, and then continue the process. So you have the original image, record image, using modified CPA, and final retrieved image. These are the results for modified known plain text. Okay. Now I'm at the last portion. So what lies beyond? As I said earlier, no commercialization has been possible because nowadays tabletop systems are heavy. These are vibration-free tables, bulk optics, and temperature stability etc. is needed. But miniaturization is possible using the concepts from nanophotonics. Ultimately, you can go to photonic integrated circuits. And there's quite extensive literature now how metamaterials can be used for generating diffractive optical elements, holographic optical elements, and various other optical components. So lasers, beam splitters, diffractive optics modulators, waveguides, all are miniaturized.
Конечно.
Incidentally, we also used optimization
Ну и
algorithms
мы
like
можем
particle
поменяться,
swap
можем повернуть камеру на вас.
methods to
Я вам там
optimize
подсуну.
some of these parameters, encryption parameters. Currently, we are exploring the possibilities of using concepts from the deep learning. There is a roadmap by Javidi and others, published in 1916, which gives certain ideas. These concepts have become somewhat old. In the meantime, the concept of deep learning is taking over. So I will repeat my I'll continue with my concluding remarks and say that various methods have been described, but as has been shown, many of these methods have been attacked, successfully attacked, and those who claim to have an unbreakable zipper system, because they cannot break it, are either geniuses or fools. Unfortunately, the current state of affairs is then there are more of the later in the. So I come to the end and sign off with this presentation and try to answer questions if any.
Thank you, Professor. Thank you, Professor Singh, for the brilliant talk.
Thank you very much.
And now we have a time for the questions. And the first questions is from Professor Valar. I give him to microphone.
Hi, dear Professor. I'd like to ask one question about your devil's vortices. The question
Is Professor Alex is speaking? Professor Moliar is speaking?
devil's vortices and encryption
Sorry,
with the help.
I'm sorry, I cannot hear you properly.
Ничего не понял.
Yeah, kindly continue.
Вот хорошо.
Shobita? Undo?
Question. Dear Keher, I asked you about shaping devil's vortices and encryption of the image with its help.
Should I reiterate the question with your permission, sir?
Yeah, please.
Yeah, the question is asking that can you talk in more detail about the devil vortex? And second question is how it increase crypto system strength.
Yes.
Okay, I'll have to go to my slide.
So how the strength of the crypto system is increased with the use of the devil vortex. This is what the question is.
Okay, there is a short answer because you have now an additional parameter available in terms of the topological charge. Is my voice clear?
Yes, sir, your voice is clear.
Я не понял.
Thank you for the answer, Professor Singh. I would like to continue maybe this discussion a bit. I'm interested also about the devil vortexes, and here for this auditory of this conference, it's most important to know what exactly introduces the adding of topological charts in new devil vortex Fresnel lens, because it contains from three components, yes, and one of the components is a topological charge. So the question is, maybe you tried the using of this system without topological charge, but with other two components. So what exactly what exactly kind of crypto systems adds exactly topological charge? So maybe I reformulate a bit a question from Professor Valar.
Okay, so I started with a fractal zone plate, fractal phase zone plate, and then a lens function, which will in optical implementation obviously involve the focal length and the wavelength being used, and then the vortex lens. So the phase function becomes a multiplication of these three factors. So you have the parameters, I had shown in one of the slides, in wavelength, in lens focal length, and then of course the topological charge now. Is it clear?
Sorry, could you demonstrate the slide if possible? How this this plate with three components?
And also I should make clear that it's not just the rotor filter of this vortex. You also have this devil's lens.
Okay, I think.
So this is the phase function. Devil's stare. And
sorry, we don't see your screen.
don't see the screen?
Yeah.
Okay, probably I stopped sharing it.
Ага, вот. Посмотри.
Is it visible now?
No, still no. Четырнадцатый. Ага.
I'm sorry, there seems to be some problem. Anyway, I'll send you some literature on this. This is all published work.
Do we correct paper that is this results is published in the paper of 2014 in Devil vortex phase structure in frequency plane mask for image encryption?
2014 applied optics and several other papers that I mentioned.
Okay. I think we see this paper. Okay, I think we need to moving forward to the next talk, and in addition we would like to thank the speaker again. Thank for the brilliant presentations. Thank you, Professor Singh.
Thank you.
And now it is my pleasure to present the next talk. It's made by Professor Kedar Khair from Indian University. From Priyanka Lochap. Indian Institute of Technology, Delhi. Yes, Professor Khair, we are welcome to present your presentation.
Thank you, Nikolai. Do you see my screen?
Yeah, we see your screen well.
Thank you. Right?
You can continue.
Yeah, I would like to thank the organizers of this meeting for this invitation. I really want to attend this meeting physically sometime, but with the current condition, this is the best we can do. I am Kedar Khair with the Optics and Photonics Center, which is newly formed at IIT Delhi. Professor Senthil Kumar is my colleague who works a lot on singular optics. I don't particularly work a lot in this area, but more recently we have taken up some work in this area. And Priyanka is a PhD student who just graduated with some interesting work that I'm showing here. So laser beam propagation through turbulence is an interesting problem for a large number of applications like defense and communication systems. Major problem in these systems is that we have to send the beam over a few kilometers at least for any practical application, and since the medium, which is atmosphere, is not controllable over this distance and also is fluctuating randomly, any carefully designed laser beam generally actually degrades into speckles and becomes unusable. And so something needs to be done when sending this beam out so that the degradation is somehow mitigated. When you think about the atmospheric correction, the first thing that comes to your mind is the adaptive optics kind of systems where laser is actually sent out and then the return beam from the target comes back. You do a wavefront sensing on that and then feed that correction to the deformable mirror, and so that if this loop is done very fast, maybe the outgoing beam is now corrected and it will have a better beam profile at the target. Now, adaptive optics is simple to understand, but it is an engineering challenge if you are going to put this kind of system out in the field. And so our interest in this problem was to see if there is any alternative way to think about maintaining a good beam profile even after going through the atmospheric turbulence. Now, I did not enter this area either from the turbulence point of view or the singularities point of view or any of these traditional approaches. But I came to this problem from a very different route. So the next couple of slides may sound like a little bit of a digression, but I will come back to the point of why these ideas are important for beam design. So I was more interested in just the complex signal representation that we use all the time for representing optical fields. For example, you may have a real valued field that you represent by means of cosine, and then create a quadrature corresponding to that field, which is a sine. And the sine and cosine are well known to be connected by the Hilbert transform. Now, the question you might ask is, what is so special about Hilbert transform? Why do we keep using sine cosine representation and not any other representation? The answer to this question was actually provided quite in old times by Leonard Mandel in a very curious and interesting paper in 1967. Result from Mandel is something like this, that you start with a real value random process, x of t, and then construct a quadrature signal, y of t, which is obtained by convolving x of t with a filter, k of t. Then a complex signal is generated as a x plus iy in the usual way. Now, if this signal represents a narrowband process, then z of t will have this amplitude and phase, the envelope and carrier kind of representation, where z0 is the slowly varying envelope. Question posed by Mandel was very interesting, that you find k of t, this filter function, which is unknown so far, such that the envelope function z0t has a slowest or least fluctuating kind of envelope. And so this is done by taking a derivative of the complex envelope function, taking the square of that, and then ensemble averaging the quantity. So we want to find a filter function k of t such that this quantity is minimized. And this problem is actually a variational optimization problem, and the answer to the problem is that k of t is actually the Hilbert transform or corresponding to a filter which is like the signum function. So the quadrature representation through Hilbert transform is the most efficient representation for the envelope. One way to understand this is that you're trying to represent one function by means of two functions, the amplitude and phase. And so there are multiple representations. And so the least fluctuating kind of representation is obtained via Hilbert transform by means as proved by Mendel. Now, how is this problem related to ours? Is that I was for quite some time ago actually interested in trying to see if this idea in Mendel's theorem can be generalized to higher dimensions, like a two-dimensional signal, because sine cosine is inherently a one-dimensional signal. But if you try to extend Mendel's theorem, what you can show is that the filter, which is equivalent to this signum filter in one dimensions, is the spiral phase filter. So the beam propagation in turbulence, then this result kind of came back to me. Now, what does this result actually mean in an optical experiment, a diffraction experiment, for example? So if you take an aperture and illuminate it with LG beams, for example, now the spiral phase has arrived there. And so the idea is if you diffract using the L equal to 0 and L equal to 1 OM states for the same aperture, then this what the Hilbert transform property now means is that the diffraction pattern for these two beams must show some sort of a complementary behavior. An example here is an experiment where we generate a CGH and display it on an SLM. And the CGH is actually illuminated by the L equal to 0 OM state. And the CGH is designed such that it makes this dot pattern IITD, which is initials of my incident. If you illuminate the same pattern with this SLM with the L equal to 1 beam or a spiral beam, spiral helical phase kind of beam, then you see that instead of each of these dots, now you have a donut. So locally, the diffraction pattern is actually locally negatively correlated. You can also see that this negative correlation extends over the diffraction limited part locally. Now, this is not, CGH is any general kind of phase mask pattern, but you can also go to more random kind of scattering kind of screens, and you see that these are then the diffraction pattern then is no longer a simple spots, but it evolves into a fully developed speckle. So these are two speckle patterns for L equal to 0 and L equal to 1 illumination of a same random screen. Now, if you just look at these patterns, there is nothing much interesting right away. But if you look at the two, if you go to the same places in the speckle pattern, what we observe is that there is a locally negative correlation. So the red pattern along this line and blue pattern is along this line. And you see that the peak of one pattern is very likely to be near the minima in the second. We thought of studying this also for random phase screens that have certain spectrum, like the Kolmogorov or the von Karman kind of spectrum. And so you make these phase screens that represent atmospheric turbulence typically, and you study their diffraction pattern with the L equal to 0 and L equal to 1 illumination. You see that that negative correlation property kind of still survives. That there is a null in the pattern here for L equal to 0 illumination, but at the same location there is a peak for the L equal to 1 illumination. Here again, there is a line of maxima, and at the same time there is a line of null at the same position. So the two negatively correlated diffraction patterns are there for two OM states. And in fact, if you try to go to an area is about the size of the diffraction limited spot, and compute the intensity correlation between these two diffraction patterns, we observe that the correlation coefficient is minus 0.09, which is very close to -1. So it's not perfect -1 correlation, but still pretty good property, which is independent of meaning it is happening on its own. So since there is a negative correlation where the minima in one and the peak in the other are coinciding, we thought that we will just add these two illuminations incoherently, meaning the speckles from these two are added incoherently. And you see that although now the phase screen representing turbulence is changing, possibly in time now, your beam profile, the central spot of the beam, actually always remains quite good in quality. So compared to the scalar beam, which shows speckle-like effects, a lot of spots, this beam does not have that kind of effect. And at least in the center, the beam is fairly uniform, which is very important for many of these applications. To understand the beam quality improvement, we developed a simple idea that we actually go to this total beam and we put circles of different radius. And then within each circle, we compute the mean intensity divided by the standard deviation of the intensity to get some sort of a beam profile SNR. As you see that, for individual scalar states, L equal to 0, 1, the diffraction patterns, these are the signal to noise ratios defined this way. But when you add these two together, what you see is that these are not independent to each other, and in fact, they are negatively correlated. So the beam profile SNR improves considerably than what you would expect from just adding two random speckles. On the x-axis of this plot, R is actually the diffraction limited spot size. So you see that again, the improvement, significant improvement is actually happening within the diffraction spot size. These results are shown over, averaged over 50 realizations of the turbulence. Since we, one of the ways in which you can do this, get these two intensity profiles to act together incoherently is to put the L equal to 0 and 1 beams in two polarizations. And that leads to what is known as polarization singular fields. For example, the lowest order C point beams, L equal to 1 and 0, are the star and lemon type of beams where here the orthogonal polarization states as RCP and LCP have been used, the circular polarization basis. Similarly, if you use L equal to 1 and L equal to -1, then these are known to create the V-point vector fields, which maybe two examples are radial and azimuthal. Our interest in this work is not so much on the polarization state. We are only interested in adding these two contributions incoherently. Although the beam we are now sending, it does have either a C point or a V point singularity. We wanted to understand whether C point, because of this negative correlation, has any advantage over the other kind of polarization singular beam. And so we looked at 4 different cases in this work in physical review A. Where first you have a scalar beam, so the RCP, LCP, the diffraction patterns are identical, and there is a +1 positive correlation. The second beam, in the second case, we introduced a Gaussian beam in RCP, and in LCP we had a hollow Gaussian beam, which is now just amplitude diversity. And you see that these two patterns, the correlation is still very high. And so adding these two patterns may not provide much advantage in terms of making the beam uniform. If you look at the L equal to 1 and -1 states, which is the V point singularity, you see that the correlation on an average over many realizations of turbulence actually drops down very fast to close to 0, although the sigma is not very small. But what it tells me is that on an average, the V point beam probably doesn't offer too much more advantage because it's now the diffraction patterns are on an average independent of each other. However, if you do L equal to +1 and 0, which is the C point beam, you see that the correlation is highly negative, which means the beam gets much more uniform. So in some sense, all inhomogeneous polarizations are not equivalent when it comes to considering the overall uniformity of the beam profile. So the C-point beam seems to offer this advantage because of the negative correlation property of its two polarization components. To verify this for more realistic turbulence, we also developed a software ourselves where a detailed multi-phase screen method was implemented, and it has all kinds of things included, which includes von-Karman spectrum and the subharmonics, and all those things are explained in detail in this article. We were trying to look at focused polarization singular beams for this case. And you see that when you propagate even up to 2 kilometers, or even you can go up to 3 or kilometers or so, if you have these realistic parameters like Cn squared of 10⁻⁻14, beam waist of 5 centimeter, 1.5 micron wavelength, and there's curvature added to the input beam for focusing it. You see that C-point still has this negative correlation property for two polarization components even after a few kilometer propagation. And so we believe that C-point beam may still offer advantage in this more realistic situation. I want to end the talk with some new work on the speckle observed with B-point and C-point illuminations. This is new work, not yet published, it is in review. The main idea is that we have a polarization singular beam generator. There are standard methods to get this kind of beams, and so the input is either a V-point or a C-point singularity. And as I explained it, it is really understood as two different fields in the two orthogonal polarization states. And so these fields are then focused with a lens. There is an aperture, and between in the focus path, we put a ground glass diffuser, which is a standard diffuser. But the point is now, when you put the diffuser, there is no longer any beam the camera. You just see a fully developed speckle. The point I want to emphasize here is again the two OM states that make the V-point or C-point singularity now see the same randomness because they are collinear in this beam. And so the resultant speckles that are due to two different polarizations, they are not really independent, but there is some correlation between them. If you look at just the camera fields, camera records, what you see is this is speckle from L equal to 0 illumination, L equal to 1 illumination, L equal to -1 illumination. Now, if you look at it again, there is not much interesting here. But if you add these two, you see that there is a very interesting sponge-like texture to this the C-point illumination-based speckle. Whereas if you add the 1 and -1 speckle patterns, basically the speckle patterns generated using L equal to 1 and L equal to -1 illuminations, you see that the speckle actually develops a very interesting noodle-like texture. And so we have kind of named these spawn speckle as speckle because it comes from C-point illumination, and we have named the noodle speckle as veckle because it comes from V-point illumination. Now, if you took in the lab, these are some of the typical records on camera. This is the scalar speckle, this is seckle and veckle. Texture to these speckles from C-point and V-point illumination. So in order to distinguish these, what we used is a standard method from the image processing literature, which is known as the GLCM methodology, or it is also called as the gray level co-occurrence matrix methodology. But this GLCM is a matrix, and the entry PQ in this GLCM matrix is actually a probability of finding a pixel with gray level P at a specified distance and angle from another pixel with a gray level Q in the given image. So this is a well-known methodology since 70s for texture analysis of image. So if you have a speckle record, you can form very easily the GLCM matrix, and from the GLCM matrix you can extract many numerical parameters which represent the texture of the speckle. So we did that. We actually extracted about 10-15 parameters and then put them into a principal component analysis code. We see is that we can clearly see the visual texture differences, and that is seen here as well. In the PCA plot with first and second principal components, we see that the speckle patterns from the V point illumination, C point illumination, and the standard scalar speckle textures can be distinguished very easily by almost even an unsupervised methodology like PCA. The possibility of distinguish the input polarization structure just by observing the speckle texture is a very interesting and intriguing result in our opinion. And particularly if we want to think about communication through randomness, then we seem to have some sort of control. So I can switch the input polarization state from C point to V point, and on the other side, I really don't have to detect any phase or polarization, but I just have to look at the texture of the resultant speckle field on the camera, and then I can tell which was the input polarization state. So there is probably a lot more new results to come in this area, but this texture analysis of speckle in this way, in our opinion, is quite new, and it has many interesting possibilities. I think my time is up, so I want to stop the talk here. So in summary, we showed that the spiral phase filter can generalize the notion of Hilbert transform to 2 dimensions. This leads to complementarity of 0-1 OM states on diffraction, and so that their intensity profile, if they, meaning these 2 states see the same turbulence, and they are focused on the target, there is going to be this negative correlation, which tells us also that all vector beams are probably not the same. C point beams seem to be more robust as far as this idea is concerned. And so again, we talked about this in terms of polarization singularities, but it doesn't have to be so. Any mechanism for incoherent addition of 2 OM states will also provide an advantage similar to the polarization singular beams, because you are essentially adding 2 intensity patterns separately. And finally, I also showed some new results on speckle and this structured light, or C point and V point light. The new finding there is that the speckles that are produced by C point and V point illumination have a distinct texture. There's a spatial texture, and that can be easily classified and maybe used as a control for any application. I will stop here. Thank you very much for your attention, and I will be happy to answer any questions.
Thank you, Professor Kher, for the brilliant talk. And indeed, we have several questions. And the first question is from the chat from Professor Forbes. I read it. Great talk. How do you know that the C point results in region of turbulence? 2 different radii means 2 turbulence strengths.
Different regions of turbulence, because the OM beam is much bigger, so it will see stronger turbulence even though the SETI may be the same.
Yes, so we have actually tried to play with, in these results we did not play with the beam waist, the 2 components, but you can actually try to optimize this by making sure that the beam wastes for the Gaussian and L equal to 1 are slightly different. So we are giving up orthogonality there, and so still meaning that may be a way to improve the negative correlation. So they may be obviously seeing the 1 and 0 states will see slightly different turbulence. I agree with that. That can be corrected by playing with the beam wastes. Is that okay?
Okay, all right. Now I was just wondering whether your result could not be explained by that fact. But anyway, good to investigate further.
Yeah.
Okay, and we here also have questions. The question is, could you please detail some parameters of turbulence, because it could be classified maybe in terms of phase range of diffuser or something else. Could you speak a bit more detail about this?
For the turbulence simulations?
Yeah.
Those are actually discussed in detail in this applied optics paper. We have used the von Karman spectrum. We have to generate the basic phase beam. On top of it, we have also added the subharmonics of phase. We have done propagation using angular spectrum. The beam, the CN squared value used is 10⁻⁻14, which is a typical value seen in across many places in India. The beam waist we used was 5 centimeters. Lambda is 1.5 micron, and we have also added a curvature to the beam so that it just doesn't actually expand, but also focuses at some distance that we design. So I think that is the parameters for turbulence. The inner outer scales are also there. For example, the outer scale is about 3 meters, inner scale is a few millimeters. Any other thing? I don't think so. So all those explained in detail in this article. Or I can pass on the article to anybody who is interested.
Okay. Thank you. I think we need to move into the next talk. Professor Kher, thank you for a brilliant talk, and we will continue the topics of the speckle optics with the talk of Professor Vladimirov from Yekaterinburg, and the talk is entitled "In Speckle Optics: Achievements and Challenges." Professor Vladimirov, please, you have a time for a plenar talk.
Так, Николай,
Yes.
Вы слышите меня?
Да.
Так, я сейчас включил полноэкранное изображение моего доклада. Вы видите его?
Нет.
Ага.
Мы видим вашу камеру.
Понятно. Сейчас. Так, сейчас?
Да, теперь видим.
Так, я выйду тогда на полноэкранный режим. Так, что-то не получается.
Показ слайдов наверху или F5?
5 нажимаю, не получается.
Ну наверху мышкой можно.
Так.
Еще чуть выше. Правее. Ага.
А тут ваша... Так. Так. Почему-то у меня не получается. Так.
Чуть-чуть правее показ слайдов. Вот переходы, анимация, да, вот это.
А вот это?
Нет, следующее.
Ага. Так, и?
Начать сначала, самое левое.
А, вот это.
Ага.
Все.
Окей.
Так, спасибо. Уважаемые коллеги, рад приветствовать вас. И я начну свой доклад. Значит, название вы видите на экране. Вы видите мою мышку, двигавшуюся?
Да.
Так, значит, эта работа представляет 3 института. Это Уральский федеральный университет, Институт машиноведения УРАУРАН, я вернее представляю, и Екатеринбургский институт вирусных инфекций. Ну и здесь приведено содержание моего доклада. Николай, каким временем я обладаю, поскольку доклады задержались?
Мгм. Ну, секундочку. Мы должны следующий доклад начать в 12.
Да.
То есть сейчас у вас есть 35 минут.
Так, ну тогда мне придется сжать, значит, исследования, достижения в исследованиях до 2010 года и в основном, значит, остановиться на наработках после 2010 года, поэтому мы начинаем. Ну, я хочу сказать вначале, что значит, после значит, создания лазеров и обнаружения спеклов в свободном пространстве и в плоскости изображения объектов были начаты исследования в области изучения статистических свойств спеклов. Вот. И значит, эти исследования были обобщены в значит, книге, которая вышла в 1975 году. И в этой книге была глава, посвященная статистическим свойствам лазерных спеклов. И предложена модель рассеивающего тела, которая формирует вот эти самые спеклы. И были предложены формулы для плотности вероятности для реальной мнимой части комплексной амплитуды, для результирующей фазы, для интенсивности и для контраста спеклов. Эта модель используется и мною в моих исследованиях и расчетах в решении задач по динамике спеклов. Ну, были получены формулы для продольных и поперечных размеров спеклов и практическое применение для неподвижных спеклов были в основном следующие. Это изучение определения статистических свойств рассеивающей поверхности, шероховатой поверхности по статистическим свойствам спеклов. Значит, в области динамики спеклов пионерской работой была, значит, работа Анисимова, Козела и Лакшина, и большое число исследований были проведены, и обзор этих исследований был сделан в 1986 году в обзорной статье Ешимура. Отдельно я хотел бы выделить теоретическую статью Ямагучи, где он теоретически рассмотрел смещение и декорреляцию спеклов для разных оптических конфигураций и предложил ряд приборов, методик для определения перемещений, поворотов и деформации поверхности. Ну, здесь приведена схема датчика определения деформации, основанная на регистрации спеклов, динамики спеклов двумя фотодиодными линейками. Ну и применение биоспеклов, которые формируются при освещении биологических объектов. Ну и существует пока единственная методика по применению спекла в биомедицине. Это, значит, методика определения регистрации контраста спеклов, плоскости изображения объектов и определения скорости потоков на сетчатке глаза или на конечностях пациента. И вот в этой 16-й работе Брайерса было дано и теоретическое обоснование этого метода. Ну и, значит, важные методики созданы на основе интерференции спекл полей. Это спекл-фотография, коррекционная спекл-интерферометрия, голографическая интерферометрия. И надо упомянуть работу Зельдовича, Шкунова и Яковлевой, голограммы спекл полей, где, значит, спеклы, понятие свойства спекла были использованы для решения задач о дифракции световых волн на объемной голограмме. Ну и они ввели понятие спеклон и кратко остановились на дислокации волнового фронта, то есть явление, имеющее непосредственное отношение к теме нашей конференции. Вот. Ну, это я опускаю. Ну и теперь перейдем к работам после 2010 года. Они, значит, это в основном мои публикации, основанные на эффекте естественной синхронизации фаз в спекл полях. Этот эффект был обнаружен где-то в 2010 году и опубликован, суть этого метода опубликована вот в статье, которую вы видите. Значит, этот эффект был обнаружен случайно при использовании интерференции двух спекл полей для определения скорости поверхностной волны релея. Здесь лазерный пучок, лазерный луч фокусировали на поверхность объекта, и отраженные спекл поля накладывались, и в области пересечения спеклов мы помещали точечный фотоприемник, который при прохождении волн релея через освещенные поверхности возмущали поверхность, и интерференция волн регистрировала вот это возмущение. Вот если случайно был перекрыт пучок, один из пучков, и на месте расположения одного из сигналов был обнаружен сигнал. Если мы перекрывали второй пучок, то на месте второго сигнала появлялся сигнал. И возникновение вот таких явлений было объяснено далее на модели, которая была использована для решения задачи о динамике спеклов, плоскости изображения отражающего и справа прозрачного объекта. Суть этого эффекта заключается в следующем. Рассмотрим область, равную линейному разрешению линзы внизу картины. И здесь располагаются точечные центры рассеивания, от которых распространяются волны со случайными амплитудами и фазами. Вот. Если случайные фазы случайным образом меняются во времени, то в сопряженной точке QR возникают случайные флуктуации интенсивности. Но ситуация кардинально меняется, если в этой области возникает либо градиент перемещения для отражающего объекта, либо градиент показателя преломления на пути этих волн. Ну, пусть этот градиент возникает в направлении оси X. Тогда, оказывается, возникает следующее явление. Среди множества центров рассеивания найдутся такие, что волны, отраженные от них, обладают следующими свойствами. Они распространяются от центров рассеивания, расположенных на одинаковом расстоянии по оси X, а Y-координаты у них случайны. И начальные фазы этих волн одинаковы. Начальные фазы одинаковы. Тогда возникает такая же ситуация при интерференции синхронизированных по фазе волн, как и в дифракционной решетке. Но теперь при изменении градиента перемещения или показателя преломления не случайное изменение сигналов протекает не в пространстве, а во времени. И оказалось, что интерференция вот этих синхронизированных по фазе волн эквивалентна интерференции двух волн, расположенных на краю вот этой области, и разность оптических путей этих волн определяется вот этим соотношением, где, значит, здесь вектор скалярное произведение вектора, значит, относительного перемещения на единичные вектора, на сумму единичных векторов, которые задают направление освещения и наблюдения. Либо это интерференция, можно интерпретировать как интерференцию двух волн, отраженных от соседних двух центров, но с длиной волной лямбда нулевое, деленное на число, равное длине волны лазера на число рассеивающих центров. И для малых увеличениях вот эта новая длина волны может попасть и в рентгеновский диапазон с соответствующими последовательностями по чувствительности и, значит, и пространственному разрешению. И вот этот эффект, на базе этого эффекта, извините, значит, были решены, с учетом, вернее, этого эффекта, ряд задач по динамике спеклов. В частности, была решена задача о динамике спеклов в плоскости изображения периодически деформируемого объекта. Мы предполагали, что вот эти центры рассеивания одновременно участвуют в трех типах движения. Значит, они поступательно перемещаются, они совершают периодическое движение, и они случайным образом перемещаются в пространстве. И мы получили выражение для средней по времени интенсивности И с волной. Вот первая формула. И выражение для временной автокорреляционной функции. Эта интенсивность, это третья сверху формула. Значит, актуальность исследований в области, значит, расчета остаточного ресурса деталей, которые эксплуатируются в условиях многоцикловой усталости, которые удовлетворяли бы требования инженерной практики. Значит, от 50 до 80% деталей разрушаются вследствие многоцикловой усталости. Короче говоря, существующие методы неразрушающего контроля не видели до сих пор многоцикловую усталость. Вот мы предложили методику, которая начала видеть эту многоцикловую усталость и количественно анализировать необратимые процессы, протекающие при многоцикловой усталости. Значит, здесь буква S обозначает, значит, разность фаз, равная волновому числу на разность оптических путей двух волн, вот тех волн, о которых я говорил. Ну, тут мы расписали, значит, скалярное произведение. И вот временная автокорреляционная функция у нас равна произведению трех автокорреляционных функций, соответствующих поступательному перемещению, это 1. Значит, экспоненте, это 2, где в экспоненте сидят дисперсия, значит, разности фаз, начальный, текущий момент времени и корреляционный момент разности фаз в начальный и текущий момент времени. И третье произведение, это косинус. По знакам косинус стоят, значит, разности оптических путей начальный и текущий момент времени, среднее их значение по ансамблю объекта. И вот корректность этих формул нами была проверена на примере прозрачного объекта. Значит, была использована формула, проверялась, вернее, формула, показанная наверху. Значит, прозрачный шероховатый объект с известной шероховатостью мы перемещали в своей плоскости. регистрировали с помощью камеры динамики спеклов и строили автокоррекционную функцию, показанную внизу слева, внизу слева. И по соответствии с формулой, если при перемещении, значит, мы перемещаемся на расстоянии больше, чем интервал корреляции флуктуации разности фаз, мы выходим на постоянный уровень, поскольку второй член исчезает, и по дисперсии разности фаз можем перейти к дисперсии разности высот и сравнить теорию с экспериментом. Мы получили отличное совпадение теории с экспериментом, и параметры шероховатости РА, найденные, значит, по динамике спеклов и по парафилрометру, совпали в пределах 5%. И мы, значит, считаем, что эти формулы корректны. Ну и эта методика была нами использована для изучения необратимых процессов, протекающих при испытаниях на многоцикловую усталость. Были испытаны вначале образцы с надрезом типа Шарпи, и по распределениям коэффициента корреляции плоскости изображения мы могли визуализировать области необратимых процессов и количественно оценивать изменения рельефа поверхности. Здесь приведены данные для образца для прозрачных объектов. Это образцы из авиационного стекла и бытового стекла. Здесь приведены распределение коэффициента картины спеклов, распределение коэффициента корреляции фрагментов спекловых изображений. И нам удалось количественно оценить изменения, относительно изменения показателя преломления и плотности, и предложить концепцию оценки остаточного ресурса деталей следующим образом. Мы определяем предельное значение физических величин, соответствующих разрушению, и в результате при контроле определяем текущее значение этих физических величин и, и по скорости их изменения можем оценить примерно остаточный ресурс этих деталей. Значит, здесь приведены результаты эксперимента, поставленного нами и опубликованного недавно. Значит, здесь нам удалось с помощью призм на одном кадре зарегистрировать 3 спекловых изображения, соответствующие 3 ракурсам наблюдения. И значит, по динамике спеклов определить области локализации необратимых процессов по распределениям, значит, величины это вдоль выбранных направлений и обнаружить область зарождения трещины. И в этой области мы зарегистрировали 3 зависимости среднего значения по времени интенсивности излучению от числа циклов. Это крайняя правая верхняя зависимость. И по ним, решая система 3 уравнений с 3 неизвестными, а неизвестными является относительное перемещение, значит, точек поверхности на базе линейного разрешения линзы в направлении оси X, Y и Z, значит, построить графики зависимости этих компонентов от времени. Ну и оценили предельное значение растягивающих деформаций как отношение дельта Y к линейному разрешению линзы. Значит, это вот 10 микрон мы должны поделить на 60 микрон. И мы получили, что по порядку величин это деформация порядка 10 минус первой степени. И по порядку величины она совпадает с предельной деформацией, которая возникает при растяжении до разрушения стандартных образцов при квазистатическом нагружении. Вот. Ну и мы сделали вывод, что все, по существу, методы неразрушающего контроля и все методы расчета повреждений методами механики сплошных сред, и все методы расчета напряженного деформированного состояния методами конечных и граничных элементов могут быть использованы и адаптированы для изучения многоцикловой усталости. Надо только учесть, что вот эти деформации локализуются в области порядка 10 микрон. 10 микрон. Вот. Это, я считаю, чрезвычайно важное достижение в области оптики спеклов и закладывает значит, основу для создания методов неразрушающего контроля как оптических для неоптических нового поколения и метода диагностики и оценки и расчета остаточного ресурса деталей, которые удовлетворяли бы требованиям инженерной практики. Вот эта методика нами используется для изучения необратимых процессов, протекающих в клетках, в живых клетках. Значит, в экспериментах мы моностой культивированных клеток изучаем. Значит, здесь показаны две пластины с клетками и без клеток. И если построить временные автокорреляционные функции для питательного раствора, это верхний график на правом верхнем картинке, и для клеток в питательном растворе, это нижний график, то можно получить выражение, вернее, величину среднеквадратичного отклонения разности оптических путей только для клеток. И вот по совпадению, вернее, очень хорошей корреляции величины сигма-у и температуры, было предложено использовать этот параметр для контроля в качестве параметра, контролирующего активность клеток. И мы недавно провели эксперименты, где выяснили, какие метаболические процессы и в какой степени оказывают влияние на формирование этого параметра. Мы клеткам добавляли различные токсичные вещества, которые блокировали те или иные метаболические процессы. Ну, вот здесь справа снизу показана зависимость сигма от времени для нормальных клеток наверху и для, после воздействия токсичными веществами внизу. И было показано, что процессы, регулирующие осмотическое давление, вносят вклад в количестве 15% в величину сигма, а процессы, ответственные за транспорт веществ через мембрану, в количестве 35%. Вот эти исследования, они обладают следующим недостатком. Здесь данные усредняются по толщине клетки. Ну и стал вопрос, а нельзя ли в малых областях клеток послойно определять вот эти параметры, определяющие параметры, а именно среднее значение, дисперсии, время корреляции, автокорреляционные и спектральные функции разности показателей для, в принципе, получено для обоих конфигураций, оптических конфигураций. Вот. И здесь, значит, под знаком суммы стоят те же самые, значит, параметры, о которых я говорил, но соответствующие разным m слоям клетки. Значит, сравнивая эти уравнения с уравнениями, полученными для параметров, усредненных по толщине клетки, мы видим, что они являются, значит, сумма вот этих параметров равна параметру, характеризующие, значит, процессы, усредненные по толщине клетки. Поэтому появляется возможность методами томографии, зарегистрировав, значит, необходимое количество уравнений, равное, значит, количество неизвестных, определять параметры, значит, вот, характеризующие необратимые процессы в послойно малых, то есть послойно на малых участках клетки. Значит, вот в этой статье и была показана корректность этих формул на примере, значит, динамики спеклов, которые возникают после, значит, помещения клеток на подложку после их разморозки. Значит, нами было показано, что здесь существует 4 основных процесса, влияющие на динамику спеклов. Это процессы в питательном растворе, процессы функционирования, связанные с функционированием клетки, связанные с хаотическим движением клеток и возмущения, вызванные контактами с соседними клетками. И, значит, зная, значит, дисперсию фаз и время корреляции для 2 процессов, и примерно определяя, значит, по зависимости интенсивности излучения от времени, значит, вот эти параметры соответствуют 2 другим процессам, мы получили отличное совпадение экспериментальной и теоретической зависимости автокорреляционной, временной автокорреляционной для временной автокорреляционной функции. Последние 2 параметра мы подбирали, значит, изменением в небольших пределах, небольших пределах. Но, к сожалению, пока у нас нет возможности, значит, реализовать вот эту томографию живых клеток. Но для случая, когда оптические разности пути малы по сравнению с длиной волной, мы получили выражение, которое при некоторых, значит, случаях, позволяющее нам, значит, при определенных, вернее, условиях выделить, значит, из сигналов, значит, сигналов интенсивности, динамики интенсивности излучения, сигналы, соответствующие процессам, протекающим с разной скоростью, с разным временем корреляции. И вот здесь приведены типичные зависимости интенсивности излучения от числа циклов нагружения, от времени для питательного раствора, для клеток в питательном растворе, турбулентного течения. Значит, сигналы, выделенные с разным временем корреляции, выделенные для турбулентного потока. Мы это делали для всех процессов. И здесь приведены, значит, типичные соотношения, которые мы получали между дисперсиями разности оптических путей и с временем их корреляций. Здесь приведена зависимость среднеквадратичного отклонения для возмущения с самым малым временем корреляции в зависимости от числа циклов нагружения в условиях многоцикловой усталости. Здесь приведены зависимости среднеквадратичного отклонения от времени корреляции для питательного раствора и для клеток в питательном растворе. А здесь приведены аналогичные соотношения для турбулентного потока. Это у нас воздух без потока. Здесь на стадии формирования потока, а здесь для установившегося потока. Ну и здесь я уже должен кончать. Тогда я уже перейду к направлениям дальнейших исследований. Заканчиваю. Здесь это создание, разработка соответствующих методик и создание физической модели многоцикловой усталости, функционирование живой клетки в норме и при внешних воздействиях и создание физических моделей турбулентного течения. Ну и нерешенной задачей у нас что-то пока является использование эффекта спонтанной синхронизации фаз-волн для определения упругих деформаций при многоцикловой усталости и обоснование спектротомографа функции живых тканей организма. Ну и здесь приведены выводы. Я не буду их читать. Они написаны на русском и на английском языке. Ну, последний пункт я тогда прочитаю. Здесь создана научная база для разработки оптических, неоптических методов неразрушающего контроля нового поколения, методов диагностики и расчета остаточного ресурса изделий, удовлетворяющих требованиям инженерной практики. Ну и можно еще добавить, что мы обосновали дальнейшие исследования по созданию методик по подбору лекарств для индивидуальных пациентов. Спасибо за внимание. Да. Да.
В питательном образце какой-то детали, как сейчас в ваших экспериментах, а как-то подумать о том, чтобы разработать мобильные устройства, да, какие-то, которые бы по месту специалист мог там применять.
Значит, спасибо за интересный вопрос. Ну, я думаю, не раскрою большого секрета, если скажу, что такие эксперименты как раз были проведены 2 недели назад с моим коллегой. Они как раз использовали наши разработки для создания такого мобильного устройства. Они на военной базе проконтролировали, по-моему, 8 самолетов, которые находились в эксплуатации, на предмет состояния остекления самолета. Ну, первые результаты обнадеживающие, но есть там и, конечно, и видно, что недостатки этого первого мобильного устройства. Я надеюсь, что в дальнейшем они будут устранены, и эта методика найдет до практического применения.
Спасибо, спасибо. Я думаю, что мы должны вас поблагодарить и передвигаться к следующему докладчику. Большое спасибо. I would like to present the next talks is for Professor Natalia Kundikova from Institute of Electrophysics of Urals Division of Russian Academy of Science and South Ural State University.
Добрый день.
Добрый.
Я включаю свою презентацию.
Экран видно.
Добрый день еще раз. Я хочу поблагодарить за то, что мне предоставлена возможность, во-первых, участвовать в этой конференции, потому что в прошлом году, когда в феврале месяце, находясь на отдыхе в Крыму, я бронировала гостиницу, я предвкушала возможность общения с коллегами в сентябре. Но вот тогда это не сложилось. И я очень рада, что конференция состоялась. Я хочу поблагодарить Александра Владимировича за то, что он внял моим мольбам, и в результате была организована трансляция всех секций, а не только вот этой вот секции, которая идет онлайн. Что касается языка, то презентацию я буду делать на русском языке. As for language of my talk, I prefer to speak Russian, but I promise to answer all questions and make all comments for my slides if it will be needed. И таким образом я перехожу на русский язык. Еще раз спасибо, еще раз приветствую всех не только в городе Ялта, но и там, где находятся участники этой сессии. И как уже было сказано, работа выполнена в Институте электрофизики Уральского отделения Академии наук и Южноуральского государственного университета. Здесь вот на фотографии находится, как выглядит Южноуральский государственный университет, примерно так, как можно было видеть снизу из окон нашей основной лаборатории, которая находится в подвале корпуса, через проспект Ленина. А здесь Институт электрофизики, но это не то здание, в котором лаборатория нелинейной оптики основывалась, это было 1987 год, институт организовывался в 1986 году, и тогда он находился в центре Екатеринбурга, а Челябинск, он находится вот на границе, оказывается, России, немножко южнее, чем Екатеринбург, если двигаться вдоль Уральских гор. И вообще Челябинск, через Челябинск проходит геологическая граница между Европой и Азией. Основатель нашей лаборатории Борис Яковлевич Зельдович. Вот, к сожалению, в 2018 году, в декабре, его не стало. Но до тех пор мы поддерживали с ним очень тесную связь. Итак, немножко истории. Ну вот все хорошо знают, что оптическое волокно работает именно потому, что наблюдается полное внутреннее отражение. И когда задаешь вопрос, какие основные законы отражения и преломления, то ответ получаешь такой, что угол падения равен углу отражения, и падающий отраженный луч лежат в одной плоскости. На самом деле это все не так, если мы более детально рассмотрим эти эффекты. Итак, 1947 год, Гуссен-Ханхен. Показано, что наблюдается для линейно поляризованного света продольный сдвиг от точки вхождения пучка при полном внутреннем отражении. Причем величина этого сдвига зависит от того, как поляризовано излучение. Вектор поляризации лежит в плоскости или перпендикулярен. Следующий эффект. Если свет циркулярно поляризован, то отраженный луч выходит из плоскости. И в каком направлении будет этот сдвиг, зависит от того, какой знак циркулярной поляризации. Что касается величины сдвига и продольного, и поперечного, то это порядка длины волны. Эксперимент и теория были сделаны Гусом и Ханхеном. Это что-то подобие такого большого волновода это делалось. Сейчас дальше подробнее немножко. Теория – это Федоров и Кристофель, а эксперимент был проведен только в 1978 году вот в особо приготовленной призме. Очень красивый эксперимент. Я на этом не останавливаюсь, а хочу подчеркнуть роль советских ученых во всем этом направлении. Во-первых, Федор Иванович Федоров и Николай Николаевич Кристофель. Николай Николаевич Кристофель – это университет Тарту. Это теоретическое предсказание того, что должен наблюдаться поперечный сдвиг циркулярно-поляризованного луча при полном внутреннем отражении. Дальше. Сергей Михайлович Рытов, 1938 год, перед войной. Василий Васильевич Владимирский, 1941 год. Теоретически предсказано вращение плоскости поляризации света при прохождении его по неплоской траектории. Но вот что касается эксперимента, то тут, в общем-то, история очень-очень интересная. 1984 год. Майкл Берри, имя которого упоминалось не раз вчера, который, насколько я понимаю, основатель вообще этой конференции, в 1984 году сформулировал свою адиабатическую теорему. И в соответствии с этой теоремой, то есть предсказано существование топологических фаз, и была теоретическая работа через 2 года, в котором было предсказано то же самое, что и в работах Рытова и Владимирского. Я хочу сказать, что работа Владимирского – это частный случай, который рассматривался в работе Рытова. Так, предполагалось, что плоскость поляризации будет поворачиваться, если свет распространяется по одномодовому волокну. И это было доказано. Но вот в 1990 год в статье Physics Today Anticipation of the Geometrical Phase Майкл Берри как раз говорит о том, что на самом деле тот эффект, который наблюдали экспериментально в одномодовом оптическом волокне, он был предсказан в 1938 году Рытовым и в 1941 году, дальше как частный случай, Владимирский. А теперь вот следующий эффект. Свет распространяется по волокну. Если мы рассмотрим вот геометрическое приближение, то при каждом акте отражения происходит, как вот было показано раньше, смещение. И это смещение зависит от того, какой знак циркулярной поляризации имеет этот луч. Естественно, что когда мы говорим о распространении света в оптическом волокне, то геометрическое приближение не работает, хотя некоторые оценки все равно можно сделать. Вот, соответственно, получается, что если свет распространяется циркулярно поляризованный, то на выходе должна быть одна картина, то есть это вот спекл поля. Но если мы меняем знак циркулярной поляризации на входе в это волокно, то что-то должно произойти. И вот действительно, что происходит? Мы визуально наблюдали течение вот всей картины с небольшой деформацией, когда переходили от левой циркулярной поляризации, используя вот эту поляризационную систему, к правой циркулярной поляризации, проходя через линейную поляризацию. Здесь представлен фрагмент той спекл-картины, которая регистрировалась, вот фотографировалась на экране. Вот наиболее яркое пятно, было измерено его смещение. И результат был потрясающий, то есть совпадение эксперимента с расчетом. Но именно вот этот вот эксперимент вместе с тем, что сделано было с поворотом плоскости поляризации, привело к тому, что был сформирован термин спинорбитальное взаимодействие изначально фотона. То есть получается так, есть оптический эффект Магнуса, это влияние поляризации на траекторию, есть поворот плоскости поляризации, это наоборот влияние траектории на поляризацию. То есть получается два взаимно обратных эффекта. И на языке квантовой оптики можно было об этом говорить как о спинорбитальном взаимодействии. Изначально это было спинорбитальное взаимодействие фотона. Встречались термины spin-orbit coupling of photon, но в результате, в общем-то, скорее всего, благодаря обзору, который был сделан и опубликован в 2015 году под названием Spin-Orbit Interaction of Light, именно вот эта вот терминология и устоялась, и в настоящий момент она применяется. Итак, значит, у нас есть влияние поляризации и траектории, и обратно. Я здесь хотела бы еще обратить внимание на годы публикации. То есть статья, основная статья, в котором описан оптический эффект Магнуса и в котором демонстрировали хорошее соответствие между теорией и экспериментом, в журнале Physical Review 1992 год. Статья «Спин-орбитальное взаимодействие фотона» тоже 1992 год. И в этом же году, в этом же журнале была опубликована известная статья, в которой доказано, что пучки могут быть, в данном случае лагера Гаусса, с орбитальным моментом. Но мы сейчас говорим о двух типах угловых моментов, рассмотрели. Поляризация и вот статья Аллена с авторами – это орбитальный момент. Но есть еще один орбитальный угловой момент. Это внешнеорбитальный угловой момент. Вот если сейчас взять вот эту вот схему, то получается, что попарное взаимодействие угловых моментов светового пучка, оно, в общем-то, и есть результат, то есть приводит к спинорбитальному взаимодействию света. Но несколько слов о том, что мы понимаем под этими угловыми моментами. Но о поляризации вообще можно не говорить в этой аудитории, все прекрасно знают, что это такое. А вот внешнеорбитальный угловой момент – это траектория. То есть фактически это описывается точно так же, как это описывается в механике. А вот внутренний орбитальный угловой момент, он как раз связан с неоднородным распределением интенсивности в сечении пучка, со спекулополями, с дислокациями волнового фронта, с топологическими зарядами, которые есть в этих световых пучках. Итак, если рассматривать парное взаимодействие вот этих вот трех типов угловых моментов света, то, в общем-то, мы приходим к эффектам спинорбитального взаимодействия света. И реально получается, вот как здесь нарисованы вот эти вот стрелочки, их должно быть 6. Лучше всего это просматривается в таблице. То есть здесь показано, вот здесь вот, что влияет, на что влияет и где это наблюдается. То есть, по сути, наблюдается, многие эффекты наблюдаются при отражении и преломлении в оптических волокнах, причем и одномодовых, и многомодовых, световых пучках, в жидких кристаллах, особый разговор об этом будет, и при рассеянии света. Но вот если посмотреть на вот эту табличку из статьи, то можно увидеть, что вот очень много работ достаточно вот в этих вот клеточках. А вот что касается влияния внутреннего орбитального углового момента на спиновый угловой момент, то мне до сих пор удалось найти только одну статью 2013 года, и она посвящена пучкам Айри. А вот в этой табличке зеленым выделены те объекты, в которых эффекты спинорбитального взаимодействия света наблюдались в нашей лаборатории. Немножко вот подробнее, где это было опубликовано, а о некоторых эффектах я расскажу подробнее. Итак, влияние внешнего орбитального углового момента на спин – это наши работы в многомодовом оптическом волокне и световых пучках. То есть в световых пучках работа, она еще не опубликована, пока только в архиве. Теперь влияние наоборот спина на траекторию, на внешний орбитальный угловой момент. Но это уже упомянутые статьи по оптическому эффекту Магнуса, а также поперечный сдвиг перетяжки в циркулярно-поляризованном излучении при смене знака. Немножко о нем в конце потом поговорим чуть-чуть побольше. И влияние внешнего орбитального углового момента на внутренний орбитальный угловой момент. Это было показано, как если волокно если волокно имеет геликеодальную форму, то что происходит со светом? И еще один момент – это влияние спинного углового момента на внутренний орбитальный угловой момент. Тогда эта публикация у нас была просто названа как формирование единичной дислокации волнового фронта. Но последнее развитие событий немножко позволяет другую интерпретацию дать этому эффекту. Итак, сейчас вот немножко побольше о влиянии спинного углового момента на внутренний орбитальный момент. И здесь то, что было сделано в жидких кристаллах, и наша работа. То есть это преобразование, фактически, по сути дела, это преобразование спинного углового момента во внутренний орбитальный угловой момент. Если рассмотреть распространение света циркулярно-поляризованного в оптическом волокне многомодовом, на выходе которого стоит четвертиволновая пластинка и поляризатор, то оказывается, что на выходе мы получаем линейно поляризованное излучение, у которого не плоский волновой фронт, а вот такой вот геликеодальный. Это связано с тем, что при распространении света в волокне происходит трансформация циркулярно-поляризованного света одного знака в другой. Поэтому наша задача была выделить просто одну единственную волну. Это делалось при помощи четвертиволновой пластинки и поляризатора, и получить вот такое вот излучение. И действительно, фактически мы получили метод генерации пучка Бесселя, который несет орбитальный угловой момент. То есть моды оптического волокна со ступенчатым профилем показателя преломления – это пучки Бесселя разного порядка. Поэтому здесь мы получаем именно пучок Бесселя. А вот замечательная работа 2006 года, когда было показано, что если взять неоднородно распределенный жидкий кристалл и пропускать через него излучение, то можно получить пучки с ненулевым орбитальным угловым, внутренним орбитальным угловым моментом. Так, первая работа, именно 2006 года, это получалось топологический заряд этого пучка равнялся 2. Позже были сделаны другие работы. Вообще вот эти вот пластинки с неоднородно распределенным жидким кристаллом, они получили название Q-плейт, о них упоминалось вчера, и они очень широко распространены и используются. Теперь посмотрим влияние внешнего орбитального момента на внутренний орбитальный угловой момент. Наблюдать это можно в оптическом волокне. В следующем эксперименте. Я хочу сказать, что наша первая работа, она опубликована была в 1995 году, ну а позднее теоретическая работа была в 2006 году. Вот обратите внимание, сейчас будет меняться шаг спирали здесь на анимации, и при изменении шага спирали будет поворачиваться спекл-картина. А теперь возникает вопрос, а если это излучение будет циркулярно поляризованным, то есть включаем спиновый угловой момент, внешний орбитальный угловой момент, и как они будут влиять на внутренний орбитальный угловой момент, то есть на вот это вот излучение. Будет меняться угол поворота спекл-картины или нет? И тогда возникает вопрос. Рассмотреть, возможны ли эффекты взаимного влияния, в данном случае вот поляризации и распространения на световую структуру пучка. То есть это как бы новый тип спин-орбитального взаимодействия света. Тогда получается сейчас, вот если мы это все вот так вот разобьем на кусочки, то у нас есть спиновый угловой момент, внешний орбитальный угловой момент, который может влиять на внутренний орбитальный угловой момент. Есть внутренний орбитальный угловой момент, внешний орбитальный угловой момент. Могут ли они влиять вот вместе на спиновый угловой момент? И последняя здесь клеточка – это спиновый угловой момент, внутренний орбитальный угловой момент. Будут ли они влиять на внешний орбитальный угловой момент? Конечно, в таблице это все намного лучше видно. То есть получается, что возможно 3 эффекта, в отличие от тех эффектов попарного взаимодействия, которых насчитывалось 6. И вот в оптическом волокне, вот примерно так, как на предыдущих слайдах я говорила, этот эффект удалось обнаружить. Таким образом, циркулярная поляризация, вернее, знак циркулярной поляризации или спиновый угловой момент, параметры траектории, в данном случае спираль, как внешний орбитальный угловой момент, вот приведет к изменению пространственной структуры светового пучка. Но возникает вопрос, какой угол можно определить, вот на какой угол поворачивается вот эта спекл-картина, какой угол можно определить. В первых экспериментах по оптическому эффекту Магнуса этот угол на длине волокна около метра составлял 1,5 градуса. В общем-то, из общих соображений следует, что угол поворота, то есть хорошо определяемый, не может быть больше размера углового размера спекла. Ну вот в данном случае было взято волокно с меньшим диаметром сердцевины, который давал больше угол смещения на меньшей длине, но тем не менее все равно это волокно из него нужно было сделать спираль. И если мы делаем спираль с очень маленьким внутренним радиусом у нас происходит деформация волокна, и мы ничего не можем увидеть. В общем, в результате для того, чтобы определить угол поворота, использовалось обращающее зеркало. То есть фактически получалось следующим образом. То есть записывалось в фоторефрактивном кристалле, записывалась голограмма, через волокно пропускалось линейно поляризованное излучение, а линейное поляризованное излучение, как всем известно, это суперпозиция право- и лево-циркулярно поляризованного излучения. То есть в результате это излучение распространялось по своим собственным траекториям. При помощи считывающего лазера восстанавливалась обратная волна, она проходила снова через волокно, и в результате мы могли видеть на экране камеры два пятна. Расстояние между этими пятнами, естественно, было равно, то есть было связано с углом поворота этой спекл-картины. То есть при разных шагах спирали, которые мы видели разное расстояние между двумя спекл, вот этими вот пятнышками, которые наблюдались на выходе из волокна. В общем, в результате, то есть направление вращения уменьшалось, то есть угол поворота уменьшался, если мы меняли направление вращения спирали. И вот для диаметра цилиндра, на который наматывалось волокно 10 сантиметров, длине волокна 65 сантиметров, то есть на этой длине и при таком диаметре спекл-картина практически не искажалась, мы видели, что вот такое вот изменение угла поворота, то есть угол поворота спекл-картины при смене знака циркулярной поляризации зависел от того, какой шаг имеет спираль. Но какие еще могут быть эффекты спинорбитального взаимодействия света? Этот вот эффект мы рассмотрели. Остается вот эта вот клеточка и вот эта вот клеточка. Здесь у нас поляризация или спин, внутренний орбитальный угловой момент. Будут ли они влиять на внешний орбитальный угловой момент? Я хочу напомнить работу, которая связана с влиянием углового момента на внешний орбитальный угловой момент светового пучка. По сути дела, эффект заключается в следующем. Если пучок асимметричный такой системе, то, естественно, мы должны увидеть сдвиг этой перетяжки. Сдвиг этой перетяжки наблюдалось при рассеянии вот перпендикулярно, то есть изначально вот в работе 1994 года использовался или раствор мыла, но в нем достаточно нестабильная спекл-картина была, или в кристалле синтетического кварца, так называемый симопал, в котором неоднородности были заморожены при фазовом переходе. Этот кристалл был изготовлен художественных изделий в Челябинске. Там вот хорошо эта спекл-картина. И тогда вот при помощи фотографирования вы представляете, что продольная компонента, она очень слабая, и требовалось достаточно много времени, чтобы ее вот зафотографировать и потом обработать эти снимки. Но вот чтобы дальше двигаться к возможности поиска того эффекта, о котором я говорила, был проведен следующий эксперимент. То есть все то же самое, только луч не обрезается, а луч проходит через верхнюю или нижнюю половинку линзы. И в этом случае тоже оказалось, это уже можно было использовать здесь при нынешних в нынешних условиях, при нынешнем оборудовании, которое есть, можно использовать ПЗС-камеру и смотреть наблюдать излучение через поляризатор, который расположен параллельно направлению распространения пучка, наблюдать специальные, в общем, потом были программы разработаны для того, чтобы определить этот сдвиг вот этой вот перетяжки. То есть все вроде нормально, все получилось. Ну, а теперь возникает вопрос. Вот можно ли здесь вот сделать так, чтобы одновременно и использовать и спиновый угловой момент, и внутренний орбитальный угловой момент, и влиять на внешний орбитальный угловой момент. Тоже речь идет о продольной компоненте поля. Ну и, в общем-то, ответ на этот вопрос напрашивается достаточно легко. То есть нужно просто использовать световой пучок, который обладает дислокацией волнового фронта. И тогда мы можем наблюдать, то есть использовать такой световой пучок и рассматривать 4 случая. Циркулярную поляризацию, левую, правую, и лазерный пучок, который имеет либо положительный топологический заряд, либо отрицательный топологический заряд. То есть на самом деле такой эксперимент сейчас в процессе, предварительные результаты получены, и действительно сдвиг перетяжки зависит и от того, какой знак имеет дислокация волнового фронта или какой топологический заряд несет этот пучок, и от того, какая циркулярная поляризация у нас не закрыта. То есть возникает вопрос, можно ли придумать такую схему эксперимента, чтобы одновременно влияла и траектория света, и внутренний орбитальный угловой момент на поляризацию.
Продольный, то есть внешний угловой момент, они не учитывают. Вот какой-то комментарий можно?
Ну вот давайте начнем с того, что для того, чтобы сделать траекторию, обычно же мы рассматриваем траекторию, у нас получается линейная. Для того, чтобы ее сделать нелинейную, эту траекторию, чтобы она... То есть когда у вас по прямой свет распространяется, то есть фактически там никакого влияния нет. И тогда мы можем спокойно говорить о том, что сохраняется полный момент, который состоит из спинного углового момента и внутреннего орбитального углового момента. Но вот как раз работа Зельдовича, она показывает, что сохраняется, и когда вот у нас есть при полном внутреннем отражении есть смещение пучка, вот там как раз там нет внутреннего орбитального углового момента, там сохраняется полный угловой момент, который состоит из траектории, то есть смещения, и поляризации. Но а в тех работах, которые мы рассматриваем, вот до последнего времени, мы смотрели или фактически два угловых момента рассматривали их взаимовлияние.
Спасибо. А вот работы по распространению пучка в свободном пространстве, где пучок при распространении, но вот из-за того, что у него там есть как раз угловой момент, он немножко поворачивается. Они как раз относятся, то есть можно считать, что это внешний угловой момент?
Возможно, но, может быть, вы мне тогда когда сошлетесь на эти работы, я не очень хорошо понимаю, о чем идет речь.
Ну, и я сейчас, наверное, оперативно сделать это не могу, наверное, я отдельно вам это потом.
Да, я буду вам очень признательна.
Хорошо, и вот есть из зала еще комментарий. Владимир Юрьевич, я, наверное, просто микрофон передам.
Добрый день. А можно такой дилетантский вопрос? А вот скажите, траектории пучка, ну как в ромбе Френеля или просто в, скажем, световоде квадратным сечением можно рассматривать как этот самый внешний угловой момент? Или это...
Можно рассматривать, да.
То есть это не обязательно в круглом световоде, это может быть действительно...
Нет. Просто, понимаете, в чем дело? Круглый световод, он позволяет задать траекторию. То есть, по сути дела, у нас, вот знаете, есть одна работа, я о ней не упоминала. Мы запускаем свет в многомодовое оптическое волокно вот под углом. То есть идет косое распространение света в волокне. И там формируется вот тоже как это сказать, не плоская траектория. И там вот тот эффект, который был сделан в работе Томито Чао, вот он фактически повторяется, когда мы выделяем определенное направление поляризации на выходе из волокна. Там темное пятно бежит по изображению спекл картины. То есть да, конечно.
То есть если взять ромб Френеля, то в нем тоже идет вот, собственно, этот эффект преобразования, собственно. Его можно трактовать именно так. Спасибо.
Да, конечно. Вообще-то интересный очень вопрос. Спасибо огромное за него. Надо подумать над этим.
Есть еще вопросы из зала. Профессор Валяр.
Добрый день, Наталья Дмитриевна.
Да, добрый день, Александр Владимирович. Вот лично вам, как сказать, глубочайший поклон и спасибо.
Вам спасибо за доклад, очень интересно, я когда-то этим занимался. И у меня сразу возник вопрос. Ну вот, в свое время Борис Яковлевич, когда я представлял этот материал, что вращение плоскости вызывает фазу Берри, а фаза Берри дает дополнительную поправку. Он мне указал на то, что фаза Берри – это уже поправка постоянное распространение моды. Ну, какой, скажем, оптического вихря. А еще вторая поправка – это уже более высший порядок. Вот у меня вопрос такой. А какая величина этой поправки к поправке, вызванной фазой Берри?
Спасибо огромное за этот вопрос. Я просто никогда сама этим вопросом не задавалась. И я постараюсь посмотреть и, может быть, вам отвечу.
Спасибо. Ну, мы постоянно на связи, и поэтому будем активно поддерживать эту связь.
Хорошо, спасибо.
Спасибо большое. Так, вопросы еще зала нет. Ну, тогда, Наталья Дмитриевна, спасибо большое за интересный доклад и за дискуссию, которая состоялась. Я тогда, наверное, постепенно переключаюсь на следующий доклад, а вам большое спасибо.
Спасибо всем.
We have a bit small time, but I think I can already announce the next speaker is Yuji Shen from University of Southampton, and the talk is entitled as Structured Light. Yes, you can speak, please.
Okay, can you hear me?
Yeah, we hear you well.
Before I start, I want to ask a question to Natalia. I'm sorry, I cannot understand Russian, so I missed the question part. I'm very interested in the classification of spin-to-orbital interaction. the sixth type. Is it published anywhere? I just could you show the published paper? I would like to read that.
Yes, it's published, and I can to present you the reference in chat, or
Okay.
I'll do it in just in some minutes during your presentation.
Okay. 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 Maybe I share my screen and try it.
Yeah. Yes, please.
Okay. Okay. Can you see my screen?
Yeah. We hear your screen. Well,
Okay.
you can
Hello,
start.
everyone. I'm Dr. Jeshen from University of Southampton. Today I'm going to talk about a structured light toward multiple degrees freedom at high dimensions. In the first part, I will show a series of exotic spatial structure light, many including my PhD works in Tsinghua University, China, and also many works made in Wits University when I was a visiting researcher there, and also cooperated with many other institutes international. Then I will show my recent work about spatial temporal structure light. Many works in Southampton, also with many collaborators with Singapore, Israel, and China. Okay, structure light refers to the arbitrary tailoring of all the degrees of freedom of light, amplitude, frequency or wavelength to shape the light in multiple degrees of freedom, right? And following this map, we can do many light shaping, we maybe combine the wavelengths and optical angular momentum, the vortex phase. We can control some wavelengths and OM tunable vortex beam from a laser, and maybe we can also combine the more spatial degree of freedom to make some vortex lattices and multi-singularity arrays. And then maybe we can even combine the more degree of freedom, for example, the time, to make some vortex pulse with tunable temporal shape and optical angular momentum. Okay, now there's a problem. Traditionally, we make light shaping always in separable state. We treat various degrees of freedom separately. There's another novel kind of state of structure light is that non-separable state. That means the non-separable state of light means the light state cannot be treated separately with various degrees of freedom. Yes, and these are main things I will introduce today. And I start with the typical example of vector beam. The vector beam, you can see the spatial mode and polarization non-separable state. Okay, the separability of the space polarization is similar to a entangled state. You can see the spatial varied polarized pattern can be expressed as the non-separable state with orbital angular momentum mode and polarization. Yeah, and this form is extremely similar to an entangled state. Right, and the entangled state recently has emerged a very important topic is that we can generate many particles to be entangled, the multi and in a higher dimensional entangled state, and so that inspires us to think a question. Can we generate the general vector beams to mimic the higher dimensional, the multi-particle entangled effect? And that may be a very important structure, general structure, and we can transfer more method from quantum mechanics into classical optics to do some quantum classical coupling research. Okay, to this end, let me have a brief review of the conventional vector beam, right? The polarization and the orbitangular momentum mode has a similar structure that can be mapped on a Poincare sphere. The polarization can be mapped on a Poincare sphere to revealing the spin evolution and the orbitangular momentum mode, the vortex evolution to reveal the orbitangular momentum. Okay, if we make an inner product of them, we can get the higher order Poincare sphere, right? And that can also be mapped on a Poincare sphere, revealing the spatially varied polarization pattern and with spin orbital coupling degrees. Okay, but the model has a limit because we always use the only azimuthal index to describe the structure mode. Actually, a laser mode actually should be described by 3 mode index: the one longitudinal mode and the 2 transverse mode. And how to reveal the general structure, and this have we deal with by previous work, and by applying SU2 transformation to revealing the orbitangular momentum evolution in a Poincare sphere with general arbitrary order Hermite-Laguerre mode, right? And more interestingly, we can further generalize this model by we know that each Hermite-Laguerre mode can be regarded as the eigenstate, as the eigenmode at free space, and we can imply the concept of coherent state. Okay, the coherent state is actually a complex, well-defined wave packet that's superposed by a set of frequency degenerate eigenstates, right? Like this, and it's a concept from quantum mechanics. If we use these two to construct a structure that will transfer the interesting quantum classical coupling into classical mode, because the coherent state has this intrinsic property. Okay, that will design the mode to with ray wave duality, the very interesting phenomena predicted by the quantum classical coupling. And then the generalized such a mode can also be mapped on the Poincare sphere, because each eigenstate can be described by a Poincare sphere. And then the new degree, we can also use the orbitangular momentum because to describe the evolution, to describe the ray caustics evolves from a planar trajectory into circular, and the orbitangular momentum describe how large is the circular twisted trajectory. And another degree of freedom is the phase, the coherent state phase, right? And this phase decides how the ray sequence distributed. You can see the marked by various color. The different phi will have different shape. Okay, how to generate? The structure, ray wave structure light can be direct generated from a simple laser. And the method is basically using the cavity shape control to control the coupling between longitudinal mode and the transverse mode. And we can see the coupling relationship directly related to the cavity length and the in a common planar concave cavity, right? And then we come to the cavity length. We can meet various kinds of frequent degenerate ratio, and corresponding to the trajectory bouncing back and forth into a periodically in the cavity. And also we proposed a new method to control the phase, the coherent phase. For example, the 1/4, the periodic fall trajectory, we can control the W shape into M shape corresponding different orthogonal phase state by exploring the bound position control and the crystal gain media control in that. Okay. There's a limit in previous work because we can only generate one trajectory mode in a cavity. We recently proved a very interesting state that we can excite two trajectories with orthogonal phase states simultaneously in a single cavity. It requires a precise control of the bumping spot. Like the bumping spot. If the bumping spot is precisely located as the two trajectory mode with the same reflecting point, that will excite such an interesting hybrid state mode, like this, the white box, the hybrid state, and we successfully generated this new state in our experiment. We can see we can control the pure trajectory state into a hybrid state, and then control the orthogonal phase, another trajectory state, and control the rate numbers in this. Also, optical momentum. The optical momentum transformation by a schematic mode converter can also be applied in our hybrid railway mode, and we can transfer the complex railway trajectory mode into the beautiful star shape, and the five star and hexagram star shapes, and carrying orbital momentum. And this shape actually revealing the ray twisted acoustic effect. We can see the modes, the rays are twisted among propagation, and at the same time we can control the vector state because the crystal we used is the C-cut crystal, and this crystal has an interesting baryon fringes effect. That means the ray's trajectory with different inclined angle will undergo with different polarization modulation. Okay, then that means the larger ray trajectory and smaller ray trajectory can be modulated by different polarization, right? And then we can modulate the scalar state and into the maximal non-separable state, the orthogonal with the inner trajectory and the outer trajectory with orthogonal polarization, right? And the other general state, and we can see the different state have different topological phase distribution in the beam, and the maximal non-separable state like a flower shape, and the scalar like a vortex, multi-singularity vortex shape, and the general, we can also have the star shape like that. The study of the phase also inspire us to design the digital hologram to generate such a railway mode beyond the limit of cavity, right? By designing the digital hologram, we can design many new kind of railway Rayleigh structure model. For example, the complex coupling between the longitudinal mode and the transfer. So we can this can generate Lissajous curves to trichoidal curves transformation mode, and this may be not easy to be generated by cavity, but that may the state from a linear array into a elliptical and a circular array, carrying a schematic effect. That's a new degree of freedom to control light. Okay. In previous result, we only generate the Rayleigh mode at frequently degenerate state, right? But if we precisely control the quasi-degenerate state, that means the cavity length slightly deviated from the precise degenerate state, we can observe a very interesting phenomenon. The various rays sport can be connected to each other to generate the polygonal vortex state. And that's a degree of freedom to control such a novel structure. Okay, actually, the Rayleigh, especially the hybrid Rayleigh structure like can allow us to design many new degrees of freedom to in light shaping. Another question, the next question, I think is more important because is how to use this degree of freedom to realize the complete high dimensional control. For example, we already know that if we have 2 degrees of freedom, we can control a 4 Bayer state, the eigenbasis for the 4-dimensional control. Right now, can we use our new degree of freedom to generate higher dimensional entangled state? For example, the 8 GHZ state for the as expanded by the 3 degree of freedom. Actually, we realized it by using our Rayleigh structure beam by selecting the 3 degree of freedom, the ray trajectory oscillating direction, and the round trip location, and the polarization. And then we design a sophisticated spatial-light modulation system to realize the higher dimensional light shaping. We can see the front end is generating a actually higher order, higher dimensional entangled state, and we can precisely shape that to arbitrary GHZ state, the maximal entangled state with 3 degree of freedom. And also, we inspired by the quantum mechanics, we designed a new state tomography measurement for the classical entangled beam. And we can actually the entangled the coefficient can be actually measured by the fringes, classical fringes detection by the each subray state in there, and the different entangled state can be revealed by the different fringes effect and distribution in free space. And we measure the fidelity of the entangled state for each GHZ state, the 8 GS state, and we can see the state has a very high purity. This is the density matrix, the theoretical and experimental measure density matrix of the 3 degree of freedom, and we can see the result is extremely similar to the description of the entanglement of 3 particle entanglement. Actually, this method has more power to be extended to generate even higher dimensional entangled state with more degree of freedom. For example, we introduce the orbit angular momentum into the ray trajectory, and we can also even generate sub-orbit angular momentum in each ray state, and that's promise the 5-party tie and the higher dimensional state. And we are doing this. This give us a roadmap to generate higher dimensional classical entangled state control. Okay, in the above result, we only distribute a spatial Rayleigh structure light. We can already generate many degree of freedom and classical entangled control. Now, I will introduce another degree of freedom, the time, to create some space-time classical entangled effect with more interesting structure light. Okay, traditionally, the light mode was treated as the space-time separable solution, including the complex vector beam. Yeah, the time is treated as separately, but there's another group of the structure light means as a space-time non-separable solution of Maxwell equations. And typical example is the toroidal pulse, the flying pulse with toroidal single cycle toroidal topology, and this pulse is very interesting because traditionally we know that the wave in free space is always transverse wave, right? The transverse wave that is oscillating behavior is like electric dipole, right? But the flying donut pulse, the toroidal pulse, it's like a new kind of electromagnetic excitation. It's a toroidal dipole. Like this, and additionally, with the propagation effect, it's actually can generate a superposed effect of electric dipole and toroidal dipole, and generate antipole structure. Right. This is a very novel electromagnetic and excitation, and will predict many new effect in light matter interactions. So that's the motivation we need to study the property of the space-time non-separable pulse and how to generate it. Okay, here is the very the foundation, the toroidal pulse. You can see the flying donut geometry topology upon propagation, and they also can describe by the two parameter. One is the cycle length, as can be seen, is nearly a single cycle structure, and actually the toroidal structure is evolving versus the time, and also has focusing described by the Rayleigh range parameters. And an interesting space-time effect of this pulse it can be described in its spectral domain. That is the iso diffraction effect. This is a very unique effect because that means the various color of the pulse, various color diffract at the same rate. The blue component is always confined inside, and the red always outside. And this allow us to describe it by some quantum-like tools. Here defines the spectral state and the spatial state. The spectral state means the the monochromatic state of light defined by various wavelengths. Yes, and you can see the like the flying donut, the flying donut is broadband pulse, right? Various color has a different location, and we trace the the maximum position of the various color to get the spectral state. And another state is a spatial state. Spatial state is general the monochromatic state of light. That means that can be defined by the location of the maximum intensity, just the spatial profile of the beam, right? The propagating, and then we can trace the different radial ratio about the state location. Okay, the ideal flying donut isodiffraction means the spectral state and spatial state are perfectly overlapped, right? And this effect, give you a lambda state is always coupled with the perfectly non-separable with the spatial state. Okay, that is extremely similar to the entangled state, right? So that's another classical entangled effect. That the flying donut pulse are perfectly maximal entangled state, various spectral state, and various the wavelength state, the spectral state, are perfect non-separable as described here. But we know that for a general pulse, a different wavelengths can have different focus. And such a tomography matrix was defined by the inner product of the corresponding spectral state and the spatial state. Then we can construct the density matrix and use many quantum mechanics tools to describe the property of the pulse. For example, fidelity. Fidelity is mirror the closeness of the two entangled states. That can be described as how close is the pulse is to the ideal flying donut pulse, and the concurrence and the entanglement formation is the parameter to describe the strength of the space-time coupling. Okay, here I show some example for ideal flying donut. The tomography matrix at diagonal, right? That means maximal entangled effect, and we can get the fidelity concurrence one, right? And after giving some noise into the flying donut, we can see the fidelity is decreased, and even and for wideband LG beam, we know that it's not a space-time coupled mode. So the tomography matrix will give a very low fidelity to describe a very low space-time coupling. As the extreme case, the monochromatic beam is just a single eigenstate that's all the factors are near to zero. So this provides us a tool to measuring the quality, the beam quality of the donut pulse and the space-time coupling strength. And we design is an experimental device to generate such a toroidal flying donut pulse. As shown in the left side, it's our conceptual setup. It's actually by the experimental generation scheme can be divided by can be designed in a two-stage process. This involves a linear to radial polarization conversion of an ultra short pulse, conventional ultra short pulse, and followed by a spatial spectral correction by a metasurface. And the metasurface is specially designed by the antenna distribution with the singular array, and each antenna at different radio position is in charge of correct the space-time coupling. And then we get the flying donut pulse. And we do the space quantum-like state tomography of the method to the pulse. We can see the experimental, after optimization, we can get very good space-time coupling of the toroidal pulse with fidelity near to 0.8. So we can argue our device can generate a very good quality of the toroidal pulse. Okay, toroidal pulse has a more interesting property because it has a very interesting structured electromagnetic field in space-time. I will show that this interesting property. Before that, I will introduce the concept of skyrmion, and I will show how the toroidal pulse can carry the optical skyrmion in it. A skyrmion is actually a topological quasi particle. It can be understood as the model with the vector texture unwrapped from a spinning sphere, right? And the topology of the vector field can be described by various topological number, skyrmion number. A skyrmion number actually means how many times the vector field can wrap around the sphere, and that can be separated into various parameters like polarity, vorticity, helicity. The polarity means the center vector up or down. Vorticity is the winning part with different vortex shaped. And here I show some example of the skyrmions with the various topological numbers. Okay, let's have a look at the electromagnetic field for the toroidal pulse, and I will show how it can carry the interesting topological quasi-particle. And the electric field of the toroidal pulse, we can see, okay, here's the center is a cycle structure at the focus, and the field is always azimuthal polarized, and various singular line and singular shells, singular circle divide the vortex points at off-axis region. Actually, the vortex point, the symmetry is cylindrical symmetry. That's the vortex points corresponding to vortex rings, right? Something like something like the ring, it's actually we know skyrmions is crystal particle with many new topological number can be controlled. So we wish to generate more kind of topological skyrmion. To this end, I generalize the model of super toroidal pulse to super toroidal pulse. In previously, the toroidal pulse solved the the finite energy assumption with the localized factor equal to 1. And this number is actually a real number, can be larger than 1. And with such a parameter play as the order to generalize the super order structure, we can see the toroidal singular structure become increasingly complex with the increasing of the alpha parameter. And such a generation like a Matryoshka-like structure, like singular shell, multi-layer singular Matryoshka-like structure. Okay, in a super toroidal pulse, we can see more skyrmions can be generated. We have know that the fundamental toroidal pulse carry the two skyrmions with different kinds of topological numbers. Well, in the super toroidal pulse, more singularities, more saddle-like singularity and vortex singularity, more saddle-like singularity is involved into the field and divided into many regions holding more skyrmions with more texture as the C3, C4, C5, C6, the four skyrmion in the pulse with 4 different kind of topologies. Okay, when we further increase the order alpha, we can observe the very interesting fractal-like pattern, right? More and more Matryoshka-like singular line, singular shell was involved in the electric field, like a fractal-like pattern, and the magnetic field, the singularity array also distributed as a fractal-like pattern, and more skyrmions are able to be observed. For example, in the same position of the pulse. So, for example, the C1, C3, C1, C2, C3, C4 across corresponding to 4 kind of skyrmion. We can see with the increasing of alpha, we not only observe the different kind of skyrmion, we also can observe a deep subwavelength features of the skyrmions. We can with for example, this skyrmion, we can see the vector reversal effect is reach lambda over 50 structure. If this structure can be controlled, that means it will provide a new kind of method for high resolution, super resolution imaging, something like technology, detection, metrology, like that. Okay, we already know that skyrmion plays a very interesting topological tools to find new structure control in space-time non-separable pulse. Actually, skyrmion has more power to be generalized. For example, traditional skyrmion is the wrapping of the vector field onto the sphere. If we slightly incline the sphere, that will place another topological transformation to transform skyrmion into bimirror. That's a very new topological quasi-particle to be observed, and this play a very powerful tool to guide our future exploration of the topological control. Can we generate even higher order skyrmion, and can we generate even complex general bimirror state to observe more kind of interesting features in our space-time non-separable pulse? It's a very forward direction to explore. Okay, let's make a summarization. Let's make a summary for the spatial structure. I will introduce a classically entangled structure light can go higher dimensional with the structure of hybrid ray-wave structure. And the ray-wave structure play an interesting tool to generate extending the degree of freedom control of vector vortex beam beyond the 2 degree of freedom. Besides the OEM and polarization, we can design many new kind of degree of freedom to mimic the entangled state. And such an interesting structure can be directly generated from a laser and controlled by a digital hologram. Okay, the space-time non-separable mode, I introduced the toroidal pulse. It's an interesting pulse because it's a single cycle, anapole-like, non-transverse, space-time non-separable, and fermionic solution of Maxwell equation. And the quantum-like state tomograph method can be used to characterize the space-time classical entanglement. And we experimentally realized the fundamental donut pulse, and we more interesting supratoroidal pulse has great resource to be further explored, and will be interesting for light-matter interaction, communication, metrology, and imaging. Thanks for your attention, and welcome to follow my website to know more detail of my recent research update. Thanks for your attention.
Okay, Professor Shen, thank you for so brilliant talk, and I think your research introduced so huge new degree of freedom of light. So I have a question. Could you please comment, is it possible to use this degree of freedom, for example, in optical communications? Because, you know, beams with orbital angular momentum finds a lot of applications in this technical area, and maybe could you comment a bit how it's possible to use these new modalities, what you have introduced for optical telecommunications?
Yeah. Thanks. Very interesting question. Actually, the OEM beam for communication is a very hot topic. It's also an OEM vector beams. It can carry the interesting structure to encode the information, and we actually have these studies by using our higher dimensional state, and the higher dimensional state. Actually, previous communication always based on the Bell state, and in quantum mechanics the larger capacity quantum communication scheme exist by using the higher dimensional GH state. So we think our scheme can transfers this similar method from quantum communication into classical communication by using our new real wave structure to further enhance the large capacity. Actually, we have some results recently, and actually we use our method to encode information. Actually, we find some advantage for the ultra low bit error rate and higher speed. Yes. So please waiting our result. We are doing that, and I'm very confident that it's a new structure to enhance the communication technology.
Okay, thank you. And maybe additional questions about temporal control of light. So you present some results about, as I understood, two cycle or single cycle pulses, yes? And
yes.
Could you please comment, is it experimental research or this is only simulations?
It's we not only simulated many properties of that, we also experimental generated such a pulse, and such a work is under review in Nature Photonics. So I didn't show the result completely. Here is a part of the experimental result. It's showing that we measure the space-time coupling of the pulse of the pulse. We can see it's very close to the theoretical single cycle pulse. But actually, I can tell you, actually, in the optical domain, our cycle is longer than single cycle, but we can generate the exact single cycle pulse in terahertz domain, and this result is the optical. You can see it's the 800 nanometer. We also have the experimental at the terahertz domain. The input is terahertz wave, and then the terahertz material, and then we can get a very perfect single cycle terahertz pulse. And yes, we can experimentally generate that, and even terahertz result is better than optical result.
Yes, thank you for your answer. It's indeed that I'm asking these questions because in optical domain or near infrared it's quite difficult to obtain single site pulses, are quite difficult to measure it, but of course, yes, in terahertz domain you're able to demonstrate these nice results.
Yes. So that's the main technical limit. It's optical domain. It's really difficult to control a single cycle structure. But we prove that even at a slightly longer cycle pulse, we can also control a very good space-time coupling. So that may be an alternative way to make some the application. The full cycle, ultra short pulse in optical domain.
Okay, thank you. And we additionally have one question from chat from Professor Forbes, and it's looks like how do you measure the MUBS in space-time? Maybe Professor Forbes could ask more detailed.
Hey, EG. I was wondering whether you any new thoughts on how to do the full tomography with continuous variables?
No, I cannot. Actually, I did a trick on the tomography. Actually, each state is not a theoretical orthogonal state, so there's no MUB. Actually, the trick I did is that I defined the state as non-overlapped. So the inner product of each state is 0. But that is actually means the state actually non-overlapped. Note the theoretical, the orthogonal like the quantum mechanics, in quantum mechanics. So
I think it's a good problem to think about, how to do continuous variables in the classical domain for a full tomography. Yeah.
Mm-hmm. Yes. If this question can be solved, I think that's very meaningful. That means more high-dimensional quantum entanglement tool can be used here.
Yeah, because in the quantum world, if you have continuous variables like you've got, then they usually do a heterodyne detection, so they wouldn't do projections.
Yeah.
So it would be interesting to think whether something could be translated across to your world. Anyway, just a comment, but very nice work.
Yes, indeed. We wish to do this. We wish to do the real projection measurement. Here, it's not the projection. It's just a measure of how overlapped of the of the two state. Actually, yes, indeed. If we can improve this, yes, that will really great improvement. Yes, we will think about it. Thanks a lot for.
Okay, if we have more questions, please ask. Yeah, we have one question from auditory. I now give the microphone to Professor Abramovich.
Thank you. Please return to the slide where the series with square root of binomial coefficient is presented.
Yes. This?
No. Series with binomial coefficient in half power.
Skyrmion or what?
No, 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 no. One of the first slides.
Wha-
Finite sum with square root of binomial coefficient. Before.
I think he means the coherent states.
No, 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 no. Before. Yes. Next slide. Yes, this formula, coherent state.
Yes.
Did you try to construct more reasonable complex ins Gaussian mode family than usual helicoidal family?
Yes.
Based on this expression.
Okay. The question is the eigen mode is selected as the Hermite Gaussian or Lagarde Gaussian. Can we use that into Ins Gaussian mode to generate interesting state, right? Yes. Indeed, we have this work, and recently accepted in Journal of Optics. And the Ins Gaussian mode will introduce the coordinate, elliptical coordinate, right? And the elliptical will generate some interesting traveling mode and standing wave mode, intermediate state between them, and very interesting thing. We have the study of using Ins Gaussian mode.
Thanks.
Okay. Do we have any questions? If no, Professor Cheng, thank you for your interesting talk. And today I need to make a short break for lunch, and we will meet approximately after 1 hour. Its exact time is 2 p.m. and 30, and we will continue with the talk of Professor Forbes. But now we are able to take some foods.
Okay, thank you.
Thank you.
Коллеги, могу потратить 30 секунд вашего времени? Не все сегодня. Значит,
Hi guys, could I just check my sound and video and screen quickly before we begin? Okay, let me share my screen. Yeah, sure, I'm going to share it now. All good? All right, brilliant. Okay, so then I'll stop sharing and I'll share again once we start the session, okay? Perfect, perfect. I'll quickly go get some.
Two of them is plenary talk, and the first talk will be given by Professor Forbes from the University of Witwatersrand, Johannesburg. A talk entitled "Structured Light Tailored for Purpose." Professor Forbes, please.
Thank you very much for the introduction and for the kind invitation to speak here. Hopefully you can hear me and see the slides okay, and let's hope the signal's fine for the rest of the talk. Right, so yes, I'm from WITS, as you heard, and in fact I just want to begin by saying that I've always wanted to come to this conference, and it's a great pity that I couldn't be there in person. You know, over many years I had discussions with Marat, and he always told me how wonderful this event was, so hopefully in the future I can be there in person and get to enjoy the beautiful scenery. But let me tell you where I'm from before I go into the technical details of the talk. So as you heard, I'm at the bottom of Africa in South Africa.
In fact, I grew up in Durban, which is a coastal town. It's where I studied at the university. Pretoria is the capital. I spent about 10 years in Pretoria, starting up a research group working on mathematical optics. And now I'm in Johannesburg at the University of the Witwatersrand. So Johannesburg at night is not such a great place and also not such a great city. But if you go outside the city, you find the suburbs. And in fact, Johannesburg is the largest man-made forest in the world. So it's very pretty. And I would encourage you to come and visit us. But you have to come back into the city to find the university. We're an inner city university. And it's pronounced V. It's a Dutch name, so it's Witwatersrand. It means rand of white water because there's a big aqueduct under the city. And next year we'll be 100 years old. If you come a little bit to the left of this great hall, you find the School of Physics. Actually, the building looks the same as this. And inside the School of Physics is my lab, and we play with structured light. And by structured light, we mean tailoring light in all its degrees of freedom, and we do that by a variety of approaches. So you just heard a very nice talk by Yi Shen, and this is actually one of his beautiful images. And he explained to you all the different degrees of freedom that one can use to tailor lights for some particular application. So let me explain to you in a simple cartoon what we do, the way I explain it to the public, for example. So the way I see the problem of structured light is like this, and I will explain it for amplitude, but the same thing applies for the other degrees of freedom. So imagine I have some blob of light, maybe a Gaussian beam, but it doesn't really matter what it is. And I want to convert it into something else, maybe a smiley face. And so the question we ask is, okay, what is the solution to this problem? What is the optical transformation indicated by this question mark that I need to convert what I have into what I want? And of course, there's two parts to the problem. The one is to calculate the answer, and the second one is to implement the answer. And usually, as we've seen in all the talks so far, the implementation and the calculation are not completely decoupled. They're always somehow related to one another. So for example, you could say, well, look, why don't you just take a piece of glass and a black pen and block out everywhere you don't want light? So block out everywhere you don't want any transmission. Of course, that will work. That's an amplitude filter, but it's very lossy. Or alternatively, we could use principles of interference and say, look, everywhere I have bright light, I want constructive interference. And everywhere I have darkness, no light, I want destructive interference. So what should the phase map be to give me this interference pattern? And of course, that you can calculate by a variety of means, and then you can implement it either as a metasurface or diffractive optics, or as we've heard, digital holograms. And you can do this principle not only for the amplitude, but also for phase, time, frequency, and of course, the polarization structure. Now, historically, we've used all of these techniques, and most recently, digital holograms written to spatial light modulators. And we heard some nice talks earlier this morning about SLMs and what you can do with them. Today, we tend to use digital micromirror devices because they're very cheap and they're very fast. And so you can just go to an old projector. It's exactly the technology that makes your projector work, probably the same one in your venue at the moment. And so the trick is simply to convert this device, which has little mirrors that can tilt. It's a very simple device. It can only switch the light on or the light off. So it has an on state and an off state. And now what we want to do is we want to teach it to be an optical device that does complete control. So what do we mean by complete control? Well, we want to control the amplitude and the phase of the lights. So how can we do that? Well, I'm not going to bore you with the details, but I can tell you that the answer, if you don't already know it, and I know the audience in this room are experts in this field, well, you need nothing more than high school mathematics, right? So we know that e to the ix plus e to the minus ix gives you a cosine x. And if we look at this, we see that on the left-hand side of the equal sign, we have phase functions. And on the right-hand side of the equal sign, we have amplitude functions. So here in this little simple equation lies the answer to go between amplitude and phase back and forward at will. And so in the optical world, of course, we can make this X whatever we want. And the plus sign and the minus sign refer to where to look. So if I give each of these phase functions that I want a particular grating, I can simply look in the correct place and find my phase function, even though the device itself can only program amplitude. So we do these sort of tricks in our lab all the time now, and we summarize it in this little tutorial paper. So if you want to get started with DMDs, and I would highly recommend you read it. And here you see below is a video made by my master's students. It shows very exotic forms of structured light, and they're all created from this very simple, cheap device. Okay, so we can create whatever we want. What should we do? What can we do? Well, I would like to go back 200 years and say that I think the first person who did structured light was actually Thomas Young. Because what he did was he passed light through two slits and he generated an interference pattern. So this is maybe not the most exotic form of structured light, but he definitely structured the light. And now with the digital approach, of course, we can do his experiments, but with more control and in more degrees of freedom. So if we were to illuminate on our digital micromirror device just two slits, we would get the traditional interference patterns. But now we can, for example, change the geometry of the slits. And here you see experimentally the image forming on the camera in real time, and show, of course, as everybody in this room knows, that as the slits become an annular ring, we start to go towards a Bessel beam. And we can change what the degree of freedom is that we interfere. So rather than linear momentum, we can interfere angular momentum. And what happens when we do that? Well, then instead of getting linear slits, we get angular slits. And so you see that both the geometry and the degrees of freedom can be controlled to structure the interference pattern, which essentially then structures your light. A question that I like to phrase to the undergraduate students is what would happen if the light passing through the two slits did not have the same polarization. So one slit had, say, a vertically polarized beam of light and the other slit a horizontally polarized light. Well, if you think about it, Young's experiment gives you darkness because the two electric fields can cancel. One can point up and one can point down. And so that means that they must have the same polarization for that to happen. So sometimes they cancel, sometimes they add, and that's why we get bright and dark fringes. And so if you have orthogonal polarization, so you have electric fields at 90 degrees, for example, then just from Pythagoras, we can see that there's no way the hypotenuse could be zero unless both fields were zero. So you can only get no light if you don't have any light anyway, which is not very interesting, right? So could you get fringes with orthogonally polarized light? So you might think no, but actually you can, and I suspect many people in this audience already know that. In fact, you have to know where to look. So rather than fringes in the intensity or the amplitude of the light, of course, what we would find in this example would be fringes in the polarization structure of the light. So this idea of interference can be taken across all the degrees of freedom. And that's what I meant in the early cartoon, that we can use these simple interference principles to structure the light at will. You just have to be a little bit creative in what you look at and where to find it. So here we had a singular optics conference. So I'm not going to give an introduction to orbital angular momentum or optical vortices because I know that you already know all of that. So in our group, of course, our favorite pattern of structured light is orbital angular momentum. So we can give the light a twist. Here you see the helical wavefronts, and of course the traditional intensity null in the middle of the beam. But on top of that, I can also change the polarization of different OAM beams. And so now I'm controlling not only the orbital angular momentum, but also the spin angular momentum. So that allows me to bring two different degrees of freedom together. We know how to describe spin on the Poincare sphere. We can have an equivalent Bloch sphere for the spatial modes. So say OAM of L and minus L on the two poles to give you complex light on the equator. So if this is the orbital component and this is the spin component, I can take the product of the two, a tensor product, and generate a higher order Poincare sphere. And now we are describing the total angular momentum of light. Of course, this is true in the parallaxal limits, but it's a very useful analogy to understand what light is going to do. So in this case, on the poles, I have the scalar OAM beams. And on the equator, I would have the cylindrical vector vortex beams, the types of beams that go down optical fiber, for example, including the radial and azimuthally polarized light. All right, so if we want to control all degrees of freedoms in the angular momentum basis, how could we do that with our simple projector? Well, it turns out to be incredibly simple because the little micromirrors are not polarization sensitive. So what that means is I can come in with light that's, say, right-handed and light that's left-handed, but at a slightly different angle. And if I engineer the grating correctly on my little micromirror device, I can make sure that the outgoing orders overlap. So for example, the first order of the two incoming beams can overlap in some region. And if I do it very carefully, they overlap in all space. And so this beam would see whatever you shape the left beam to be and whatever you shape the right-handed beam to be. So here you have a vectorial beam that can be tailored arbitrarily as you wish. And here you see some examples of structured vectorial beams using this simple device. And you can confirm, so I think the bottom row is the theory and the top row is the experiments, that in fact the polarization structure is what you designed. And so you can see that the structures that you can generate are arbitrary and at will. How high can you go on these devices? Like how complicated a beam could you really make? Well, using orbital angular momentum as an example again, we can show you theoretically and experimentally that on a typical lab device, of course, it varies a little bit from lab to lab, but these days, most devices are fairly similar in their specifications. So on a typical lab device, you can get up to about 600 in orbital angular momentum, and that we can confirm by measurement. So you see it's very, very accurate. And here's the experimental beam. And you can get about 200 different structured light modes of the same device and still have a very high fidelity above 80%. So I would say that that's quite versatile control, that you can do quite a lot with very simple devices. And so you can do it very cheaply and very fast. But of course, it's not the only way to structure lights. There are many, many other techniques, and here are some of my favorites. You know, if you're recording this talk, you can have a look at the references later, but everything from interferometers to spin orbit optics, metasurfaces, Sonia's group even showed with very simple glass cones, you could make vectorial lights. So there's a lot of methods out there, and I guess everybody chooses their favorite approach, right? And what would we do with this structured light once you've actually made it? What would we do with it? Why do we make it? Well, of course, it gives us unparalleled ability to push the limits, particularly in applications. So for example, we can increase the alphabet of our communication systems, both classical and quantum. We could do sub-wavelength focusing by structuring the light for the optimal shape at the focus. We can extend the range, for example, in light sheet microscopy, much further and wider fields of view. And we can use it for imaging. So not only on the creation side, but on the detection side to see things that would otherwise be too small to see at optical wavelengths. And we all know that this has given rise to fantastic functionality, including single molecule imaging, optical trapping and tweezing for control of the nanostructures. And here are some beautiful images from a colleague of mine who works at TRUMF for high power structured lights for laser materials processing. So he's using all these exotic forms to bevel materials and get cleaner cuts and to go deeper into those materials. So that's a little bit of an overview on what you can do and why you might want to do it. Let me zoom in at this stage to a couple of practical examples. And I'm going to start with one of our own examples quite recently. So here's an example of where structured light could give you an advantage over what I will call unstructured light. And by unstructured light, I mean light where you haven't really tailored it for the application in mind. So if you think of the Doppler effect, it's very hard to measure the speed of something. In fact, we can't measure the speed of something directly, right? We have to measure either a distance and a time and divide them, or we have to measure a frequency shift and infer the speed. So we always infer the speed, we never measure it directly. And the Doppler effect lets you get the speed of an object, but only coming towards and away from you, not the direction. You can't tell whether the object's moving left or right, or forward or backwards. So we don't have the direction. And why don't we have the direction? Well, it's because the field that we illuminate in itself doesn't have any directional information in it. And the frequency shift itself holds no directional information. But we can change that. So what would happen if we, instead of a scalar beam in our Doppler experiments, we use a structured vectorial beam? Well, you can see in this little cartoon, without doing any math, that if a particle were moving around this structure, of course, not only would the frequency change, but the polarization that it sees also changes. And if it reflects that polarization, so you can detect it, well, then you have some extra information. And if you do the math, it turns out that if you reverse the direction of the particle, the signal that you get is different. It has a phase shift. And in fact, the left and the right-handed components, their shifts go in opposite directions. And so you can use this to tell the directional information of the particle. And so the way it works is that you simply illuminate what you're interested in with your structured beam. And here in this particular example, we have a pendulum. So we have a particle moving in a pendulum. We illuminate it with a vectorial beam. And we look at the return Doppler signal, but this time for both polarization components. There's a couple of technical tricks. They're not so important. But by looking at the two components, I can get a relative signal. It looks quite messy. But if you look carefully, what comes out is that the two signals have different shifts. One goes positive and one goes negative. And so here we have information both on the direction and the speed. And so, for example, in our little pendulum, we can tell exactly where the particle is. So you see, we knew where the particle would be from theory, right? So we could calculate where it should be, and we can measure it with the Doppler effects. And we can get the angular velocity out. So you can get the velocity in all three coordinates. So now we have an enhanced Doppler effect for complete velocity profiles by simply structuring the way we illuminate the thing we're trying to measure. So that's one example of where structured light gives you an advantage. Let me give you another one, and this time I'm going to pose it as a question. And it's very interesting because this morning we heard from Professor Singh, and what he was saying is that photonic control has advanced tremendously over the decades. And of course, I agree with them. But it's also good to reflect on how far we still have to go. So if you think about it, we can put billions of operations on a tiny chip in the electronic world. But we can only do a few operations in the optical world, and typically it takes hundreds of elements on something the size of an optical table. Of course, I'm simplifying the problem. You can do integrated circuits that are optical, but in general, our optical control still lags far, far behind our electronic control. Photonics has got a long way to go. And let me give you a concrete example of this. So how easy is it to structure an electric current? Well, in the electronic world, it's trivial, right? You take a piece of wire and you bend it to whatever shape you want. And that will be the shape of the current. Very, very easy. What about in the optical world? It's very, very hard, right? Because we can change how much current we've got by changing the amount of light, for example, say on a photodiode, but we can't really direct the current. And the reason for that is because we're not using all the degrees of freedom. We're really only using how much light do we have. And that's how our devices respond. So how could we make them respond to other degrees of freedom to sculpture the electric current, but by optical control? So this work was done very recently by another group, by Paul Corcombe's group, and I really like the paper, so I'm going to describe what they did. So they took their little photodiode and they miniaturized it, down to about 20 micrometers by 20 micrometers. And then they illuminated it with two fields. And one field was at frequency omega, and the other one was 2 omega. So the second harmonic. Why two different frequencies? Well, they showed that in fact, if you look at how the electrons go in from the valence band to the conduction band, if you come in with two different pathways, so one is a 2-photon pathway and the other one is a single photon pathway, well then just like this idea of interference from Thomas Young, here we have quantum interference, but in the pathways. And this is generally referred to as coherent control. And so by controlling the relative phase and amplitudes of these pathways, you control what the net effect is in the conduction band. And what they showed is that you can transfer the spatial structure from the lights into the electron's momentum density. And that means that you can control the currents. And that's what they show in this little example. If they have a linear beam, if both beams have the same polarization state, they get currents that simply go up. If they polarize the drive beam, which is this one, the 2 omega beam, then they can get azimuthal currents or radial currents. And in fact, you can show that you can have currents in arbitrary directions. So here they're going from arbitrary points on the left to the right through weird structures to generate currents in any direction. And it doesn't have to only be in X and Y, but in fact can be tailored with the relative phase of these two beams. And so this is a really cool example of how we can bring in light's degrees of freedom, the structure of light, to structure the electronic world. But you note that the tricky thing is how to use those degrees of freedom. So in this case, it required a non-linear process and a little bit of physics to understand how that might work. And so I think that just as an example of the polarization fringes, where you need to know where to look and how to think about it, here too, you need to know where to look and how to think about it. But it is always possible. And the question that we have to ask is, well, how many degrees of freedom are we really using? Are they the correct ones? And could we do better? And in fact, I always tell my students that if I was starting out now, I would think about structured light and nonlinear optics, because I think it's a largely untouched topic. And I'm talking about converting structure from optical fields to optical fields through nonlinear processes, from optical fields into matter, Bose-Einstein condensates, semiconductors, and so on. There's a lot of work to be done, and we have hardly scratched the surface. Well, I want to come to the second part of my talk, and I'm going to stay with the nonlinear example, and I'm going to choose something that we've worked quite a lot on in the last few years. And so, of course, we are very interested in lasers. If you know anything about our work, you'll know that we've done quite a bit on designing structured light lasers. And in fact, everything I know about it is summarized in this little review article. So if you haven't had a chance to look at it, please have a read and see what you think. So could we tailor all this light, excuse me, but at the source? So rather than do it outside the laser with our spin optics or our digital micromirror device, could we do it directly where we want it? So here's my cartoon of a laser. It has the three essential elements, right? It has a gain medium. You need to excite the gain medium, and then you need a resonator made by these two mirrors. I'm going to use a simple Fabry-Perot geometry to illustrate the point, but of course you can change this to whatever you want. And what we want to know is, well, what could we do inside the box? Maybe in terms of the pumping, or maybe in terms of the special optical elements that we put in, so that the light that comes out of the box already has the desired structure. Well, if you've been in lasers for a while, then you will probably be thinking, well, this has already been done, right? Because if you look back at the early papers on lasers, and I'm thinking of people like Fox and Kolgalnik and Lee. By the way, Tinye Lee was a student from my university before he went off to Stanford for his professorship. So these guys, of course, already did this. So what they did was they used the simple idea of an amplitude mask that I showed you earlier, to control the light. So we all know that if I have a simple circular aperture inside my laser, I can laser on a Gaussian beam. But then if I put little wires, for example, inside the cavity, I can generate the Hermite Gauss beams. So this would be amplitude control to control the state of the light. And this was done in the 60s already. A nice, very modern example that I quite like is by the group in Munster. And what they did is they used control of the gain medium to control the laser mode. So we all know that loss and gain are opposite sides of the same coin in the laser. So you can control either to control the mode, right? And what they did was they used a little digital micromirror device, exactly the device I showed you earlier. And they changed the pump shape to shape the gain. So the pump lights, instead of going straight into the laser, bounced off the little projector. They shaped the pump, which then shaped the gain to some desired profile. And then they showed that the lasing mode, of course, matches the gain. And so this is another way to reproduce the results of the 60s, but with modern technology. All right, what about my favorite type of structured light? So orbital angular momentum. Could we generate orbital angular momentum directly from the laser? Well, you might think, well, why don't we do what they did in the 60s, right? If I take my mirror and my black pen, why don't I just block off the center part of the beam? Because here there's no light. So if I do that, then I can maybe get a ring of light that gives me orbital angular momentum. But that doesn't work. And the reason it doesn't work is that if you look at the +1 and the -1, and it doesn't have to be 1, so plus and minus L, in orbital angular momentum, they have exactly the same beam radius. They have exactly the same radius of curvature. The radius of curvature is not dependent on the mode order. They have exactly the same Gauss phase. Everything is the same. So nature cannot tell the difference between plus or minus 1. And so when you do that, what you usually get are these petal structures. So you get a bunch of petal-like light coming out of the laser. And the reason you get petals is that, of course, if you add a +1 and -1 OM beam together, the superposition gives you fringes in the azimuth. And so we have petal-like light. Back to our cosine beam, essentially. So it's quite paradoxical that in order to get these beautifully symmetric beams, you actually have to break the symmetry inside the cavity. And there are lots of ways to do that. You can do it in solid state lasers. I'm going to show you a couple of examples of that. You can do it in fiber lasers, and people have also done it on chips, so down into the micro world by controlling light. So let me give you a couple of examples of how you might do it, maybe one of each case. So here's a lovely example by the Kim group in Korea. And what they noted is that, look, the +1 and the -1 OM beams, their pointing vectors have got slightly, they've got different angles as they propagate. And so they simply put a little piece of glass inside the cavity. Well, if the angles of the pointing vectors are different, then the Fresnel reflection will be different. And so the one will have a higher loss than the other, just by rotating the angle of the glass plates. And so by doing this, they could tune the helicity of the cavity from the +Ls to the -Ls. More recently, a group at the CNRS in France, they used topological photonics to make microstructured devices. So you see the structure here is the order of 4 to 5 micrometers. And by using topological principles, they could show that by designing this very carefully, depending on whether you pumped it with a left or right-handed spin beam, so left or right-handed polarization, you could get a plus or minus handed OEM coming out. So this is helicity control by the pumps control. And something I don't think has been published yet by the group in Nanjing, I quite like it. It's actually an OPO cavity. And what they did was put an intracavity spin orbit coupler. And what they showed is that in this cavity, so now we have a nonlinear process inside the cavity taking place. that you could get very high purity OEM beams and high purity radial modes. So not only azimuthal control, but also radial control. So another nice example of how you could control the OEM inside a cavity. Our own work in this field started back some years ago, and what we showed is that, look, you can actually use geometric phase as your controlling mechanism. So if you build a cavity and put a spin orbit optic inside it, in this case a Q-plate, then depending on the polarization state that comes into it, so the spin orbit effect will give you a different orbital output. So how do you control the spin state? Well, that's easy. We just use a quarter wave plate. So a combination of a quarter wave plate and this Q-plate allowed us to generate orbital angular momentum with controlled helicity. So here you see from this laser a +1 beam and a +10 beam. And we could go from a -1 and -10 as well. But then if you look, we've got these two plates. And if you think about it, I could rotate the quarter wave plate, which would change the incoming polarization state. I can also rotate the geometric phase elements. And if I change the geometric phase element, I also have a net phase change. Well, two rotations, that's exactly what I need to move around a Poincare sphere. And so what we could show is that by just rotating these two elements, you could move everywhere on this higher order Poincare sphere. So if we tuned by the two rotations to be on the pole, we would get pure orbital angular momentum beams, either the plus or the minus. And then if we rotated the elements to go onto the equator, we would then get vector beams. So we get the vector vortex beams going all the way around every single possible state by simply rotating, no realignment of the cavity. And so just to give you an example, if I tune to, say, this point over here, then I have the radially polarized beam. So these are all experimental images. And you see indeed the beam is radially polarized, and we can confirm that by a bunch of tests, right? So, so we have perfect beams. And, you know, after we did this, we were very happy, of course, but then we realized, you know what, there's something strange about these beams. And that is that the net orbital angular, not orbital, sorry, the net angular momentum is 0. Because, you know, let's say the L that's left-handed is -1 h bar per photon, and the right-handed is +1 h bar. Well, they add to 0. And the OEMs, it's -L and +L. They're also going to add to 0. Imagine that's -5, then that's +5. So it always adds to 0. So could you make a beam from a laser that doesn't add to 0, where you have a net angular momentum? And so fortunately, this problem was solved external to the laser by Federico Capasso's group. And what he showed is that in metasurfaces, you can basically make the propagation phase polarization dependent. We know that the geometric phase is polarization dependent, but you could make the propagation phase polarization dependent too. That gives you an extra degree of freedom to play with. And that allows you to couple arbitrary orbital angular momentum states to arbitrary polarization states. So for example, +10 to an elliptical state. So that opens up a lot of possibilities. So we designed a structure which they very kindly made for us. You can see the beautiful experimental images of their nanostructured materials. I like to think of this as structured matter for structured lights. And in our particular example, we wanted an element that would couple +10 OEM and +100 to a left and a right, a horizontal and a vertical polarization state. So complete asymmetry in the cavity. And here are just some beautiful experimental images of their structures. And if you look carefully at this, you can actually see the windings of the phase. And this is going around 100 times. And the bigger ones are the 10 times. So very, very nice phase elements. We built this into a cavity. So this is what it looks like. Again, just two mirrors. We have this meta surface sitting inside it. In fact, it works in the green. So this had to be a green cavity. And out should come this asymmetric orbital angular momentum beams. We call it superchiral light because now we have +10 plus 100 with a horizontal and vertical. So we have a net angular momentum of 110 h bar per photon. So we can simulate how the cavity should work. And then we can do it experimentally, which is what you see on the left. And so we can again move across the sphere, but this time the pole is OM of 10, horizontally polarized. We can scroll all the way around inside the cavity by rotating the metasurface. And to the other end, we get OM of 100 vertical states. So it works very beautifully. And then something that this community will enjoy and know very well, the algebra of optical vortices, of course, is very strange, right? So 5 plus 1 is 5. What do I mean by that? Well, we made the laser have a +1 state and a +5 states. And then of course, they overlap quite strongly. And so we find these vortices. And of course, the vortices can be explained in that you get the +1 in the middle, and the peripheries is the 5 minus so L2 minus L1, so it's 4. And so we have 4 vortices. This is predicted already for 10 years by Kiko Galvez, but now we can show that these complex states of light can come directly out of the laser. So that's the state of the art in terms of what we are able to do. And I'd like to end with just one last quick example, which is our latest work in collaboration with a group in Italy. And so the idea was, look, so far we're generating single beams out of the laser, but is it possible to extrapolate that and make arrays of arbitrary structured lights? And so we built a very simple cavity. It's simply just 2 mirrors, the one on the left here and the one on the right, separated by a telescope. But instead of having the telescope matched to the mirrors, we displaced the back mirror back by 1/4 of a Talbot length. Why would we do that? Well, you will know then that in the round trip, we'll have 1/2 of a Talbot length, which means that all of these little microspheres will couple into one another. And so here we had a metasurface array exactly at this plane. After 1/2 Talbot length, we have coherent coupling between all the little metasurfaces. So every single one of these little spheres is a little metasurface. If you zoom into it, you can see the phase structure, the desired phase structure. And if you zoom into that, you can see the nanostructured materials to do it. So this is a very sophisticated metasurface that has 10 by 10 essentially OAM generators inside the cavity, all coherently coupled by a Talbot effect. So you can confirm that this works. And I won't bore you with the details, but essentially in the first design, the element all had the same charge of L1. And you can see that all the signals here for every single element of the array is L1. And you can do this for the OAM beams of +1, -1, and you can generate superpositions by controlling the polarization again to get radially polarized and azimuthally polarized beams, but this time not a single beam, but an array of structured beams like this. And you can see what the arrays look like, very complex patterns of structured lights. And this cavity has a very nice property, and this is going to be my very last slide. And that is that if you introduce the deliberate defects into the array, so over here, we've made all the array +1, except for this one, which is +2. And what happens? Well, the coherent coupling allows you to overcome the defects. This is the principle of non-Hermitian systems, that the defect will self-heal itself. And here, simulation reveals that as the round trips pass back and forward, the defect becomes back to the same as the underlying array. And we have confirmed this experimentally as well. So the message I want to leave you with is that there's a lot still to be done in terms of control, both external and internal to the laser. And with that control, I believe that there's a huge amount of possibilities for applications. Well, let me conclude then by saying that I didn't get to say anything about our quantum work. We have a recent review out on structured quantum light. If you'd like to read a bit more about it, then I encourage you to have a look. And if this talk was a little bit too fast for you, we have general reviews on lasers and, of course, general structured light. And quite recently, we put together a nice review article which summarizes what I think is the state of the art in terms of pushing the limits with structured light. What can you do? What have we done? What are the open challenges? So if the talk's been a little bit fast, then please go and read the article. If you can't get hold of it, just give me a shout. I'll send it to you. I think on that note, I'm going to conclude. Most of the experimental results you've seen, of course, were done by my students. So I have to thank them. We love to collaborate and have visitors, not in COVID times, but in normal times at least. So please do pop around and visit us if you can. And if we're a little bit too far for you, then visit our webpage. You can find out more about who we are and what we do, and perhaps we can get something started. And so on that note, thank you very much for inviting me again, and thank you to the audience for listening.
Talk. Yeah, and now it's time for questions. If any question from auditory. While the listeners thinking, maybe I ask questions. Could you please comment on the possibilities of creating a J-plate, but not from metasurfaces, but maybe from the other approach? For example, by liquid crystals or series or by fringing devices, something like that. Is it possible? How do you think?
Yeah, that's a good question. Look, in principle, it may be possible. What you have to look at is the underlying physics. You have to see whether you can make the propagation phase component polarization dependent. That is the underlying physics. If you have another mechanism that will do that, then it will definitely replicate what the J-plate does. So I think it would. What I don't have the answer yes or no, but I can tell you that that's what you need to satisfy, and it's worth looking. It's definitely worth looking. I don't believe that metasurfaces are somehow magical things. I think they just happen to be.
Okay, thank you. Maybe the other questions? Okay, I think we don't have any more questions. Thank you for a brilliant talk.
Good.
Thanks. And now, sorry, Professor Voller.
Я забываю сказать вам, что ваши доклады могут быть опубликованы как в компьютерной оптике, так и в нидерландском журнале «Сенсоры». Я там, к несчастью, topical editor. Сенсор.
Швейцарский.
Да. Я чуть перепутал.
За 150 тысяч.
Special issue, апрельский номер.
MDPI. За 150 тысяч.
Yes. I would like also to duplicate the announcement of Professor Voller. He just told us that our participants will have opportunities to publish papers and Computer Optics Journal, and there is also special issue in Sensors Journal, and our information is located on the website, so please check it, and we are welcome to your submissions. And now we are approaching to the next talk, and it will be given by Professor Yashar Azizar Kavandarag, sorry, and from Gazi University, and it's entitled Airy Beams from Fundamentals to Applications. Professor Azizan.
Do you have my voice?
Yeah, we heard you.
Okay,
well.
Just know I am sharing my PowerPoint slides, and do you have the slides in the screen?
Yes, we see your screen.
And how about the video?
We see the beginning of the presentations.
Okay, okay.
So I think everything okay. You can try to start.
Okay, fantastic. I congratulate you, all the members of the organizing and scientific committee of the conference at the Crimean Federal University and also Samara University. And I a special thank to the Professor Voliar, Alexander Voliar. It was a great and interesting initiative that the conference is holding both in person and online. I'm Yashar Azizian, as you said. I am a faculty member of Photonics Department and Photonics Research Center at Gazi University. Ankara Gazi University is a leading university in education and is one of the oldest university in Turkey, located in the capital of the Ankara. This is the main building of the Gazi University, which was designed and made by Mimar Kemal ad-Din. And this is the view of the one part of the city. And as I said, I am working at the Gazi Photonics Applications and Research Center. It is also located in the main campus of the university, and more than 13 people are working in this laboratory under the supervision of Professor Dr. Süleyman Özçelik. This picture, the left picture, I took yesterday with the students and some of colleagues which are worked in this laboratory. And just now I would like to introduce, maybe in our last conference you was introduced about this laboratory, this research center. The base of this research center is on the base of thin film technology and crystal growth, and there are some advanced facilities in the field of the optics, spectroscopy systems, and crystal growth system. It is located in this center, and there are many opportunities for future to have some collaboration, have some scientific works. This center is established in the year of 2000 at Gazi University, one of the most active center at the university and also at the country also. So we have newly established photonics department at Gazi University with undergraduate and graduate students which will in the field of photonics, which will be entered to the university from this semester in physical in person. We hope we have a good start at this educational system both in this slide. I want to show some of my collaborators in Iran in my past university which I worked there. Here I was responsible for setting up a university in Iran, in the north of Iran 1 year ago, and for 6 years I worked there. I established different educational and also research laboratories. These are one part of my collaborators, which contains faculty members, PhD students, and also the master students, which I would like to thank first of all to them to help me and to be in communication, scientific communication with me. So I want to switch to my slides, and I want to start with the Nobel Prize winners in the field of optics and light. The first Nobel Prize, I gathered this information, this statistics 3 years ago by searching about the people, about the scientists, which the first one is William Röntgen, about the discovery of the X-ray, and then much more people you can see here, which they are worked directly in the field of the optics and of the electronics and light-based technologies. I don't like, I'm not going to show something about the importance of light and importance of light-based technology, because everybody knows, non-physicist people, non-scientific people also knows about the importance of the light and light-based technology, because light and light-based technology are in the daily at the home, in the daily tasks of the people. Just now, I would like to focus on the a subject which I thought about that. These people works on the interaction of light and matter, and focused by focusing on interaction of light and matter. They have much more founding about the science, and they have some great roles for developing the science and engineering. But it is very interesting, which there are very limited people have thought about the nature of light, about the existence of light, about the structure of light. I hope you have attended the great talks which presented by Professor Yiji Shen and also Professor Andrew Forbes before me, and they talked about the degrees of freedom of light. And actually, I at that time I'm skipping and deleting some of my slides. I would like to say here about the structured light, about the production of the structured light, about the type of the structured light, and also about, as an example of its structured light, I would like to focus on airy beams and the applications of airy beams, and also different properties of airy beams, and some experimental results and some numerical simulations of airy beams. As Professor Forbes and also Professor Shen talked about, showed the very good image, very brilliant image in the presentation about the degrees of freedom of light. Yes, it is very important in all cases. Just I am talking to the students, because I know there are some students attending this conference, this seminar, and just know it is very important to identify the degrees of freedom of phenomena. What's the phenomena here? The phenomena here is light. The color of light is, or frequency of light. The energy of light is important. Polarization, also spin angular momentum, orbital angular momentum, and also the radial modes. So we are familiar with the electrons and photons. It is a simple picture. Why we are considering about the electrons? Based on Abel's law, the resolution of the microscope is limited by the wavelengths of the light or matter, and numerical apertures, of course, are tricks. In this picture that you see the photons has no rest mass and no charge, and has spin on 1, and it is an interesting story, spin 1. And but what is the spin of 1? But we are not going to talk about the spin here. And if you use visible wavelengths of about, for example, 500 nanometer, so you compare it with the electrons microscopies, electrons has a mass and has a charge, and also wavelengths, of course, depends on. So you can increase the resolution of your microscopes to see the fine structure, and it is on using the image. It is very important. Here I bring two images, the left one and the right one. The left one is taken by the electron microscope system, and the right one is took by the photon microscope or optical microscope. And you know what is the reason to detect the fine structure using these systems, tooth systems. So now let's assume the electron is traveling in the specific direction with specific energy, and around the specific energy and momentum, we have P, momentum, and also energy. Then you can try. So I am saying that I'm looking for an electron beam which is propagating along Z direction, has a certain energy and has certain momentum, and it means you are looking for such a wave as a solution. If you replace it for Schrödinger equation, you will get another equation only for envelope that is here we have U, R, and Z, which it is very familiar for the people that are working in the field of optics, which is the paraxial wave equation. And you have different solution for this paraxial wave equation. You can have a Lagrangian mode here, plane waves, Bessel mode, Mathieu mode, and I will discuss more about these type of the modes and this type of the structured lights more. Assuming that you have free electron and you want to solve it, for solving the free electrons for Schrödinger equation, I am neglecting the spin and neglecting the relativity regime as well. And if you want to solve this, you should use this equation, and here you have the Helmholtz equation. By solving Helmholtz equation, you can have plane waves and Lagrangian modes, Hermite-Gaussian mode, and orthogonal and complete modes. So here I want to skip these slides. Here Andrew completely in his great presentation discussed about these devices, some devices which with references he described this quarter wave plates, how we can change the polarization, what's the mechanism of the half wave plates, and different diffractive optical devices, and the effects of the angular momentum, the differences between spin angular momentum and orbital angular momentum, the applications of the spin angular momentum and orbital angular momentum. And there are some optical devices look like axicon optical lens, double vertex axicons, and also spiral phase places and some Q plates. We are all familiar with them, with these devices, Q plates. And most important thing is in this case here is a spatial light modulator, which is very important. Just now I would like to switch to a spatial light modulator and also holography system. Yes, it is true. This is the Singular Optics conference, and we are not going to talk about the mechanism of the spatial angular spatial light modulator. But just know, I'm going to introduce the student some optical device, some optical setups, which important in both research and education. To entering to the laboratory, it is very important for the students. There are some differences between different governments, different countries. You know, there are some developed countries. Some people started, for example, 13 years ago. But it is very important to set the laboratory and with maybe you don't have any money, and the cost of these devices are very high, then it is possible for you to skip the experiments, your interest or not. It is very important to you to find a rule to create a setup to understand very basic things. Just know I am going to show you some very simple devices, and very simple optical setup to enter and then understand the structured light, and then you can after understanding you can develop your mind, your laboratory, and do some advanced experiments using advanced devices. Okay. Here I'm showing you a very simple Mach-Zehner devices, and just before Mach-Zehner devices, I want to introduce something. I would like to talk about some fabrication of some grating systems, like for structured light, for understanding the meaning of the structured light. I'm starting with analog photography system. If you want to fabricate some grating systems, you are familiar with different grating systems. We have Rankine grating, we have triangular grating, blaze grating. You can make using a very simple code used in MATLAB and Mathematica in Python these grating systems, and you can take the analog photograph from the monitor of these systems, and you can develop the films with the analog photography system. And after developing, you can prepare very simple intensity grating, and you can do some experiments using the simple Mach-Zehner systems in simple interferometry systems on these gratings, and you can check the experimental obtained results and available theoretical results. You can bleach the films. You know, we have here, this is very tricky experiment. There are different types of the films. You can maybe at this time it is very hard to find these old themes. This is films which not in bazaar, and there are different type of films with different grain sizes, and it is very tricky. If you want to find the best one, you should find the best one and control the quality of the experiments. By bleaching the films, you can remove the grains, silver grains inside the film, and you can change the intensity grating to the phase grating, and you can do some experiments with phase grating. I prepared these analog hologram systems and checked all the experiments and checked with the theories, available theories, and both of them confirms together. In the case of the SLM, it was very hard to me setting up the university and setting up the laboratories. There was many costs for setting up the university, and we also want to set up some other devices. We would like to have the SLM, digital holography system. You know, the system is very simple, but the device is it's not very low cost. And by changing the using, it is very similar. The working mechanism of the SLM is very similar to normal video projector systems, and you can extract the LCD of the video projector system and use the video projector LCD as SLM system. Actually, there are many differences in quality of these homemade SLM systems with the commercially available SLM systems who look like HoloEye, look like Hamamatsu, and so on. But we do some experiment using this system, and we create some structure like here using these systems. So in this slide, I would like to introduce different types of bezel beams, different types of structure lines. I would like to start with bezel beams, then Hermit gauss, and some examples about the applications of these type of beams, and also fabrication of these beams using the systems. The time of emergence and introduction of some structured beam came back to approximately 3 or even 4 decades ago, including Gaussian, Lager Gaussian, Hermit Gaussian, Bezel Gaussian beams. In this slide, you can see the different types of these beams, and these beams have different technological applications. First one is bezel beams. Bezel beams first introduced by Durnin in 1987 is important because its non-diffractive properties. Bezel beams are formed by linear combination or superposition of the infinite numbers of plane waves, which these wave vectors could create a cone around the z-axis. Then the interference of the waves provides the plane of the stable transverse field distribution, which this calls or described as Bessel function, or the first type of zero order Bessel beams. The zero order Bessel beam distribution of the this beam has a high intensity central nucleus. The differences are here. I make there are some differences between. This is not Lager Gaussian beam. In other slide, it's a mistake here between Lager Gaussian and Bessel beams. But there are differences in the case of Bessel beams. We have a very dark singularity in the center of these beams, and also among the beams here I mentioned the Lager Gaussian beam, which, like the Bessel beam, is also a vortex beam. Was first beam to be shown to carry orbital angular momentum, and this beam is widely used in the optical manipulation and optical tweezers, micro and nanoparticle trapping systems, and in microscopy and different areas of science and technologies. Also, there are several research works which discussed about the properties of these beams: self-healing, self-focusing, self-accelerating, and different types of properties of this type of beams. There are some other beams. You can hear the name of the Inns-Gaussian beam, parabolic beams, Matthew beams, Piercy beam, and also Airy beam. The parabolic beams was introduced in 2004, is derived from the exact solution of Helmholtz equation in a parabolic cylindrical coordinate system. This beam is also one of the beams that are non-diffractive and maintain for their intensity in distribution direction. There are several papers indicate that parabolic beams have the self-acceleration properties. The generalized type of parabolic beams was introduced in 2018, and after 1 year, different types of generalized parabolic beams were introduced by Professor Kotliar. I think he is in this conference also, and also Professor Hunina, and also the fractional parabolic beams also introduced by them. Then this last one is airy beams. Just in the second part of my presentation, I would like to focus on the airy beams. The airy beams, but before this starting, I would like to say producing of this beam, all of this beam is important for us. The hologram of this is the hologram of the airy beam. This is the real picture which we get first with the SLMV, homemade SLMV prepared. You know, this hologram is we have in nature the example of this hologram also, and also this is a computer simulation of this type of Laguerre-Gaussian beam using that hologram. We prepared computationally for getting a particle and transferring a particle by the angular momentum of these beams. This is the picture which we get first at the laboratory. The student works on this using the homemade devices. He was very surprised when he understand the theory and experiments confirms together, and then these are also different patterns which we have prepared in the laboratory, different holograms using homemade SLM systems. And there are just now I would like to focus on the airy beams. Airy beams as an example of the DAT beams. Every types of beams have different properties, and these beams in these 13 and 14 years introduced by many of scientists. Just when I was talked with different people, Professor Hunina, Professor Kotliar, and Professor Volyar, Andrew, and Professor Sabino Chavez, to write something, review papers in the field of the self-healing properties of the beams, classical beams. I found different ideals in the mind of the scientist, and I think there are some things we should focus on and work again about the experiments, and talk more, and also review the papers again, and because to clarifying something about the well-known phenomena, for example, self-healing, self-reconstruction, the relation between non-diffraction beam and self-healing. Is there some relation between geometric optic, and what's the origin of the self-healing? Is it dependent? For all of these things, we need to quantify these properties. There are some papers which claim that this type of beam have, for example, basal beams have self-healing properties, but and also some other papers say that Laguerre-Gaussian beams also have self-healing properties, but the self-healing properties of Laguerre-Gaussian beams in comparison with basal beams is low. Some papers say that the Laguerre Gaussian beam are not non-diffractive beams, and there are something should be clarified in this field. Just know I'm focused to clarifying these properties, the terminology, using the terminology of, for example, self-reconstruction, self-healing, and other terminologies. For example, I'm focused on airy beams, and in the case of airy beams, I would like to discuss a little about these topics. Our group published 2 or 3 papers in optics journal, which the concept was about the quantification of self-healing properties of the beams, Laguerre Gaussian beams, and also Bessel beams. And this quantification, I think, is very important. And the degree of the similarity, degree of the self-healing should be quantified with using the different exact physical and mathematical methods. Airy beams was introduced by Berry in the year of 1979. These beams are separable answer to the paraxial wave equation in Cartesian coordinates. This beam is a non-diffractive beam also, and not only can restrict to the diffraction during the propagation, it accelerating along the parabolic direction. Self-acceleration is one of the most important features of this beam, and the beam can be self-accelerating even in the absence of any external potential. Unlike previously known non-diffracting beams, which have a 2-dimensional and 1-dimensional transverse intensity distribution, the airy beam has both 2-dimensional and 1-dimensional transfer intensity distribution, and is not the result of the conical waves. So just know I would like to introduce a typical airy beams. A typical known airy beams has no symmetry in rectangular coordinate, but if its wave function is obtained in a cylindrical coordinate system, it will have a circular symmetry. Thus, by extending the ordinary airy beam wave function from the Cartesian coordinate system to cylindrical, a new type of its airy beams it is produced, known as cab or circular airy beams. Actually, as the beam propagates, its intensity profile accelerates towards the center of symmetry, creating a parabolic caustic surface. This surface created on axis because a high intensity self-focusing point with high intensity. So the self-focusing properties of beam is due to the structure of the beam. It is it may be used for the nonlinear optical applications also. So here the title is dual and quad airy beams, and beam symmetry eliminates the need for the special experimental optical setups have their own complexities, such as selecting a specific direction between the beam and particles, especially when manipulating or guiding several micro and nanoparticles at the same time. Therefore, the production of beam with structural symmetry is of great importance. In order to achieve these goals, various research works have been done, and one of them is related to introduction of the new types of airy beams called dual airy beams and quad airy beams. In fact, these airy beams are obtained by superposition of 2 or 4 airy beams with different directional acceleration respectively. And these airy beams, these type of airy beams which have a rectangular symmetry, and these neo beams also have self-focusing properties. Another way to create symmetry in the airy beam's intensity distribution is to convert the beam nature. The beam intensity distribution is to convert the beam wave function to an even function. The beam created in this way is called symmetry airy beams or SAM. A comparative study between 2 symmetrical airy beams and dual airy beams shows that the symmetrical airy beams show better non-diffractive properties during the propagation. There are some other airy beams which introduced, and other applications for these airy beams was introduced. Also, for example, one application is curved plasma lattice. Is the symmetrical airy beams is more efficient because it has higher intensity contrast and greater self-focusing. And these beams compared to the dual airy beams, these type of beams is easier to use in experiment and requires less experimental equipments. So another type of airy beams which introduced in the year of 2018 is elliptical airy beams. As the name of elliptis, the beams has an intensity distribution with an elliptical symmetry. A circular airy beam is a special case of this type of beam, is that this beam is self-focused at 2 points in the propagation path. The self-healing property of the beam is it is very important properties which we can get some information from self-healing properties. The self-healing is the ability of the beam to reconstruct the distribute intensity and the distribution during the propagation, which allows it to regain its original intensity distribution in a non-disturbed state. This feature of a beam is very important, and there are many technological applications. These features of beam is widely used in various scientific fields, such as microscopy, optical manipulation, optical trapping, and guiding of the particles in optical tweezers and some other microscopy, and also quantum information applications. So this is the setup. I think I have 5 minutes for my presentation. I skip these slides. There are some works which focused on the self-healing properties of airy beams. There are here you can see in the left, in the right hand, the airy beams. The left hand in A, the main loop of the beam obstructed by a obstruction by a mask, and after propagation the beam shows the self-healing properties here. And also using the pointing vectors, there was simulations and studies which confirms the results. And here there are no quantification on this in comparison between, for example, the degree of the similarity of this picture in comparison with the main picture and other pictures, and how we can prove that the quality of self-healing is important. You know, self-healing, why? The question is that why self-healing is important, because we would like to keep the information, all the information using light, which is stored in the light in quantum information, for example, science. And it is very important to completely self-heal the properties, or making some structured light with different properties to have a very, very good and complete self-healing properties. Then these are also different works which published in the field of the self-focusing, self-healing, and self-accelerating of this type of being. Here, Huygens, there are two methods. It is familiar with all of you: Huygens convolution methods and angular spectrum methods for propagating and study the properties of the beam in the direction path. There are some simulation which have done with one of my master students in Kerman University, which to study the self-healing property of elliptical airy beams. You can see the video here. This is the simulation. The Z is the optimum distance which we have found the best self-healing. The similarity function, it is the quantification, and also the self-healing value. The self-healing value is a ratio of the similarity value of the perturbed and unperturbed in optimal plane to the initial plane of the beam. So the second one is the simulation about the self-healing properties of elliptical airy beams, a comparison with the elliptical airy beam with different masks. We change the morphology of the mask. For the first one, we used the circular obstacle, and the second one we use the rectangular obstacle, and we checked the effect of the mask shape and also the size of the mask on the self-healing properties. And also you can see in this video we can see the self-healing properties also in this case also is good, but we can compare using calculating these parameters, these properties with each other, and then we can talk and discuss for the interpretation and the reason of these effects. So this is the self-healing properties of this slide, the self-healing properties of airy beams, and also the self-healing properties of the circular airy beams with rectangular mask or obstacles. And the number of the this number shows the self-healing ratio. We are just the bad cases it is 1, and the best cases it is far from 1. Yeah, and in comparison with using this parameter, we can calculate the percentage of similarity between different methods of which I said in the previous slides. So this is the calculation part, and also we have some recommendation, some proposal for changing the structure of light by superposition. For example, in the case of Logger Gaussian mode, we use the superposition of different Logger Gaussian mode to improve the self-healing or other properties. And then we checked by the number, by the quantity, these effects. So the time out, I think, just now, and thank you very much for your attention. And at the end of my talk, I would like to thank to all of the people which helped me, and also all the organizing and scientific committee at the Crimea Yalta. It was very good for us, which I hope in the future we visit the beautiful city of Yalta again. And just now I want to invite you, all of you, for our third conference. I think our third conference, ICLLT, International Conference on Light and Light-Based Technology, third ICLLT, will be held in Ankara city in person, physically, on the May of 2022. Formally, we will announce the web page and the announcement within 1 month, the announcement of this conference. Just informally, just know I invite all of the people. And thank you very much for your attention again, and if you have any questions, and yourselves.
Thank you, Professor Azizian, for your interesting talk and for invitation on your conference. Okay, we now have a time for several questions. So if there is any questions from auditory or from Zoom, I see already one. I just read it. Can it use else function except ARI, and does it give similar results?
Again, please.
Can it use else function except ARI, and does it give similar results? It's printed on the chart.
Can I see the question? Just no, I don't have any.
It is located in the chat.
I am opening the, yes, I am opening the chat box here. Can I see else function except ARI, and does it give similar results? Yeah. Yes. It depends. For example, the question is that maybe, as I understand, maybe the similarity of functions between ARI beam, Logger Gaussian beam, and other Bessel beams, which same results. We all know there are some non-diffractive beams, and also some other beams. The number of beams which have different properties in the case of the diffractive optics. Maybe there are some the similarity function of the Bessel beam and also ARI beams in some cases is same, but we should check it before at first but see by simulation and then confirm it using the experiments. Yeah.
Thank you. Do we have any questions? I also have questions. It's similar like previous, but in your talk you compared several ARI beams, and maybe could you summarize what kind of ARI beams is more resistant to the beam blocking? And it's maybe first part of the question, and the second part of the question is related of the discussion what we have in previous day of the conference. It's relate what could you comment maybe what kind of special parts is there special position of the mask impacts of the self-healing properties, because of course there is a external beam structure, and maybe how it's related with the self-healing properties.
Yeah, thank you very much. It is a very interesting question. As you say, we quantified here the greater value is 2.2, and this is the best one. But approximately the results in these three cases, elliptical beams, circular beams, and is near together. But this one, in summary, this one, the 2.2 one is the better, the best one in the case of the self-healing properties. It means that elliptical airy beams is better than circular and other beams in both rectangular and circle masses. And a second question, but we should discuss about the reason of this, why the electrical physically is better, is the best one. And also we can improve by changing in this. The second question, I think, as I understand, the position of mass
Yes.
and also the position of mass in the lobe of airy, and also the size of masks affects on the self-healing properties. Yeah, it also affects. These three parameters can change using by changing the position of mass and also the size of mass and also the shape of mass. Yeah.
Okay, thank you. Do we have any questions? If no, we would like to thank the speaker again. Thank you, Professor Zizan, for interesting talk. And now we are approaching to the last talk on these sessions. It will be made by colleagues from Zuyev Institute of Atmospheric Optics, Russian Academy of Science, Siberian branch, and it will be given by Makenova Naila Аутернхановна.
Николай, можно делать, как говорится, полный экран? Вам там хорошо видно, да? А мы здесь глаза портим.
Это от докладчика зависит.
Не, ну его варианту надо ему попросить было, чтобы... Зачем нам смотреть, какой будет следующий слайд, когда мы не видим тот, который он рассказывает.
Окей.
И фактически он полностью весь доклад читал. Ну что это тут интересного в таком докладе? Причем ни одной своей работы нет. Вообще,
была. По-моему, концовка как раз вот это.
Ну, там я приглядывался, но там не было ни одного.
Sharing, because the next participants unable to switch on screen sharing because now it's done by you.
Что-то не идет, наверное.
Совместное использование синенького. Экран.
So, do you hear me?
Yes, we hear you well.
Naila Makenova is here right now, but I am the co-author of this report, and if you don't mind, I want to present it. My name is Fyodor Kanев.
Sorry, we don't see your screen at the moment. We see only the black screen.
Black screen?
Yeah,
What I see?
maybe could you relaunch it again or try to share another window? I think maybe relaunching will help.
Yes, switch on Russian. Please. не видит экран, только черная.
Попробуйте перезапустить.
Сейчас, 1 минуту.
Угу, спасибо. Пока не видим.
Мы несколько раз нажали на демонстрацию экрана.
Вот подсказывают с техподдержки, что надо выбрать окно.
Ну, мы выбираем окно.
В каком? Там либо весь экран, либо определенное окно с презентацией. То есть трансляцию всего экрана.
Сейчас. Сейчас видать?
Нет, к сожалению, все то же самое.
Николай, может, ты их принудительно включишь? Вот демонстрация, которая зеленая. Или это их экран, да?
Это их, да, я не могу. Не получается?
Подскажи им тогда, пусть они зеленую включат.
Но у нас уже 3 окна открыто.
Ага. Может быть, файл
почему-то у
присутствует?
нас все показывается. Единственное, что наша демонстрация так приостановлена написано.
Еще раз попробуйте. Попробуйте еще раз, там может быть что-то.
Сейчас еще раз попробуем.
Ага, ага.
Так. Снова у нас ваша демонстрация экрана приостановлена у нас диагностика.
Почему?
Наверное, интернет
Ну вот
зависает.
коллеги говорят, что с нашей стороны не могут тоже ничего сделать. Может быть, файл прислать и перещелкивать с нашей стороны? Да, может быть, тогда попросить вашу презентацию прислать. Вот здесь можно в чат прямо ее скинуть личным сообщением, либо на мой аккаунт, либо на Акимова Яна, правильно? Да, на Акимова Яна вот личным сообщением пошлите в оргкомитет.
Так, и ее закрыть, наверное, когда наша есть.
Там вот чат.
Да, мы сейчас в чат пришлем.
Ага. И можно выбрать, кому послать.
Кому послать? Посылаем кому?
Акимова Яна.
Акимова Яна.
Или Алекс Валяр.
Просто моя директория держит. Компьютер.
Компьютер?
Моя директория, локальный диск C и Канев. И сети нет. Где-то внизу. Файл. Дальше. Давайте я найду.
Вот может Ялту закинем, нет?
Ну давайте Ялту заходить. Есть там 3? Только 2? Нет. Тогда не надо. В моем ищите.
Вот Канев.
Ну, ищите файл ППТ.
Просто в директории?
Угу.
Вот, все нашла.
3?
Да.
Все, отправлено.
Вот, подождите, еще грузится. Все, мы отправили.
Угу.
Яне Акимовой.
Одну секунду, теперь мы его сейчас запустим.
Угу.
И тогда переключать, просто будете говорить и
Да, тогда будем говорить.
перещелкивать.
Если просто демонстрация экрана.
Получается.
открыт. Да нет. Так, запустили, что ли?
Сейчас видно, только окошечко надо свернуть с участниками.
So, I can begin? Можно начать?
Максим, можно? I think yes.
So, let's begin. First of all, I want to thank organizers of the conference for possibility to deliver this report, and I am very sorry for inconvenience with the beginning of the report. And as to speak about report, I want to discuss two problems associated with optical vortices. First of all, I would like to say several words about algorithms of vortex registration. It's the first problem. And secondly, I would like to consider the possibility to obtain optical vortices in a beam with initially smooth phase profile. So let's begin. So optical vortices. And next slide, please. And here is the formula that allows us to set optical vortices in a beam, in Gaussian beam. X and Y is coordinates of the in the plane normal to the direction of propagation, and xn, k, y, and k is coordinates of vortices. So these coordinates can be set randomly on or regularly. So let's continue. Next slide. Some properties of optical vortices that we can use to register them. First of all, as you know, circulation of wave gradients or local tilts is equal to 2 pi if the contour along which we calculate the circulation includes optical vortices. So if we obtain 2 pi calculating plus minus of course 2 pi calculating circulation, we understand that we have a vortex in a contour. Secondly, if we have a vortex in a beam, in phase profile we observe a phase cut, and this phase cut ends at the position of a vortex. It's another possibility to detect a vortex in a beam. Next slide, please. Next. So, some examples. Laser beam, it's a result of simulation, and here we can see the profile of laser beam. In the center we have a vortex. The upper picture corresponds to the first order vortex, and the lower one to the second order vortex. But in both cases we can see a dark spot in the center of a beam. So next property, we have minimum in the position of vortex, minimum of amplitude distribution. Next slide, please. Another properties. Vortex beam and ordinary beam. As a result of interference, we obtain branching points in the interferogram picture. And here we have two interferograms. Both interferograms were obtained experimentally. And the first one in the left part of the slide corresponds to the second order vortex, and to the right part of the slide again second order vortex, but here we observe some distortion of laser beam. As a result, distortion fringes of interferogram. Continue, please. Next slide. Movement of vortex in a beam. Again, it's numerical experiment. It's well-known properties, but later I will use them to find vortices in a beam. So, two vortices with the same topological charge, and these vortices move in opposite direction. As a result, we obtain such trajectories in the center of the slide and some changes of beam amplitude. And here you can see two vortices in a beam. But if we put vortices of different charges in the beam, they move toward each other. It's lower picture in my slide. Next slide, please. So, beam with two vortices, beam with 6 vortices, and now 10 vortices in a beam. And this beam propagates, passes some distance, and instead of 10 vortices, we can find only 6. It's upper picture. But if we put more vortices, not 10, but 15, after some distance, we can find 21 vortices. So, number of vortices can decrease or increase, and it is impossible to say exactly what number we obtain after some distances. Next slide. So, some simple conclusions. Coordinates of vortices changes if a beam passes some distance. Vortices can annihilate, and if a beam has complex phase distribution, additional vortices can appear in the wavefront. So, it is impossible to say if number of vortices increases after propagation or decreases. Next slide, please. The situation reminds me the book about Alice in Wonderland, and namely the situation with Crooked Party, and here poles is hedgehog, mullets, flamingos, and gates are cats, and situation changes every minutes. And the same is true for vortices. Situation changes if the beam propagates. Continue. Next slide. From the point of view of adaptive optic, as you know, special field of optic, and in adaptive optic we try to compensate atmospheric distortions of beams. And from the point of view of adaptive optic, vortices have negative influence on effectiveness of adaptive correction. This problem was illustrated theoretically in the paper by David Fried. Continue. Next slide. So, registration of vortices. First of all, we know that in interference pattern we obtain branching of fringes, so we can use this property to detect vortices. The possibility was discussed in the paper, presented in the slide, and the author developed an algorithm based on wavelet analysis, but we used different approach to the problem. Next slide, please. So we take experimentally obtained interference pattern and find all maximums and minimums in this pattern. We obtain great number of points. blue one correspond to minimum and red one to maximum. Too many points. So we applied some filtration of the image. After that, the number of points decreases. Next slide, please. And all these points were combined into lines. After that, we detect a structure corresponding to optical vortex. And then we can say that we have a vortex in radiation. In such a way, we can detect number of vortices in a beam and also position of vortices. But you can say that what is silly method? We can just look at the interference pattern and say that here we have second order vortex. But it's simple situation. Continue, next slide, please. But if we have more vortices, not one, but many, and we obtain such interference pattern, it is impossible to say, impossible to find with naked eyes all vortices in distribution. But using our program, our methods, we can find all vortices that we put in the beam. And again, here we are dealing with numerical experiment, but nevertheless, we have five vortices. And you can see and decide yourself if it is possible to find all vortices in this picture. Next slide, please. So it is the first method, processing of interferogram. But this method has lower resolution, and in all our calculations, we were able to find only 14 vortices, not more. If we put more vortices, we just lose them into the picture. So it's the best our result and obtained in numerical experiment. And I also want to tell that this method can be applied in real laboratory experiment. Next slide. Next slide and the next method. Calculation of circulation of local tilts or gradients. As you understand, local tilts of a beam can be obtained with the use of such device as Hartmann sensor. And gradients can be calculated theoretically or in a computer program. And to calculate gradients, we can use the formula given here. And here the formula for next formula is for calculation of circulation. And if the result of calculation is 2 pi plus minus 2 pi times n, where the n is natural number. So if we obtain 2 pi, we can tell whatever is a vortex in a contour. Next slide. Next. And we built a distributed computer application. So several interconnected programs. The first program is the model of beam propagation. It's a client. And also we included into the application two sensors, two servers. First of all, the model of a sensor, and one more model is the model of detector of vortices. And also we can exclude a shock-hardened sensor out of this distributed application. In this case, we need to use not local tilts, but gradients of wavefronts. So sensor is optional. And here in the picture, we can see the interface of the program, distribution of local tilts, calculated using the model of sensor and the model of beam propagation. Next slide, please. Here is interface of the program with excluded sensor. Next slide. Next. And characteristic of precision. We put 20 vertices in the beam. Coordinates of vertices were given by random numbers. So it was the first realization of random process. Then we changed it randomly, coordinates of vertices, and obtain another realization of the process. And in such a way, we calculated 1,000 different realizations of a random process. And we tried, in all these realizations, we tried to find these given 20 vertices. And in some examples, we calculated exactly 20 vertices. But sometimes we obtain only 19 or even 17 vertices. And here in the left picture, we can see the mean number is approximately 19. And also we can see confidence interval. So we try to find 20 vertices in the beam, and not always successfully. But then we applied the condition, we introduced the condition in our program. Vertices should not be too close to each other. Not closer than 1.05 or then 0.05 initial radii of the beam. And in this case, with this condition, we calculated all vertices from 5 to 14 without any mistakes, with zero interval of confidence and zero variance. So the method is precise, but vertices shouldn't be too close to each other. Continue, please. Next slide. Another method, the method number 3. So the method was described in a paper presented in the slide, and it consists of the following. If we calculate 0 points in the distribution of real and initial parts of the complex amplitude of laser beam, so we need to take real part, we need to take imaginary part, find all zeros in these two distributions, combine all these points into lines, and calculate intersections of these lines. And each intersection corresponds to a singular point in a beam. It's illustration of the method. Continue. Next slide. So we realized this method in our computer problem. Of course, it is very simple to obtain a real and imaginary part, to find 0 points, but it is difficult to combine all these points into lines. But we succeeded, and also we find intersections of these lines, and in such a way we find all singular points in the wavefront. Next slide, please. And again, characteristic of precision. Practically, we obtained the same result as in the previous example, but here we have variance greater than 0, and we have some intervals of confidence. Not always possible to detect all vortices in the beam using this method. Next slide. And the last and the fourth, our method, we try to find the point when where the phase cuts and we build corresponding computer application, but we wasn't satisfied with the precision of the method. So it's illustration of the method application. Next slide. And now the conclusion. Conclusion to this part of the report. We built computer programs simulating 4 methods. First one deals with interference pattern. Next, calculation of circulation. Then intersections of lines. And the last, ends of phase cut. And have a look at the list. The first can be used in the first and second can be used in laboratory experiments, but the first method has low precision, low resolution. The second and the third can be used in numerical experiments, and both methods guarantee practically the same precision, and the fourth method can be discarded. So we build and compare 4 methods of the vortex registration. But maybe it looks a little silly to build 4 methods, but we have such notion. We assumed that if the 4 or at least 3 methods give the same result, these results are reliable, and because of which we built several methods. Next slide. And now, some examples of the method application. We try to understand if we set the phase of the beam by some continuous function. For example, by Zernike polynomials, if we obtain singular points in such a beam, and we build such a computer experiment, we set a phase at the plane z equals 0. The phase was prescribed by Zernike polynomials, different polynomials, of course. And after some distance, we tried to find vortices in the beam. Next slide. Next. And have a look what we obtained. Oh no, previous. Oh, this one. Have a look. We set a phase using comma, and after some distances, we obtain all these images. Distance increases and distribution of vortices changes. But it's only one method, and we are not sure that we are right, but all these vortices are really exist. Next slide. Then we use several methods. Have a look, left picture. Calculation of circulation, the most precise method. Next picture, vortices were obtained as a result of lines intersection. And the last one, the right. Vortices as a branching points of interference pattern, but only the upper part of the beam was considered in the last example. And all in all, we obtained the first two pictures are practically the same, and the last picture remains the upper part of the first two pictures. So I suppose it is possible to say that vortices really develop in a beam with initially smooth phase profile. But of course, it's only a numerical experiment. So we need to obtain more proof by doing real experiments. Next slide. Next. So previous picture was illustrated how vortices can be obtained by setting a phase by comma, and now different polynomials from 1 to 36. Have a look. The first several, 2 tilts, focusing, and 2 astigmatism, and 0 number of vortices in a beam. After that, increase, here we have comma, I suppose 6 and 7, then trefoil and so on, and we obtain some vortices in the beam. Curves differs because the region where we find vortices increases from curve to curve. Next slide. And now dependence of distance. Left picture. Curves and polynomials. Number of polynomials are shown near the curve. 6 and 9 correspond to trefoil with different orientations. 7 and 8 to commas. So we are speaking about left pictures, and we can see oscillation and decrease of the number. It's simple. But the right picture, here we can see again oscillations, but it is impossible to say that number of singular points decreases. So the result of all these problems with polynomials, the lowest, if we set the phase by such polynomials as tilts, focusing, astigmatism, we don't obtain any vortices in the beam. Comma trefoil gives us some vortices, and the number of these vortices decreases. But higher order polynomials, it is impossible to say that number of vortices decreases or increases with the distance passed by the beam. So here I need to stop. That's the end of my report, and I want to say thank you for your attention. That's all that I wanted to say. Thank you very much.
And now I think we have time only for only one questions, because we need to start to the poster sessions. And do we have any questions? Yeah, we have one question. So I will give the microphone.
На русском можно?
I think yes, maybe in Russian. It's okay.
In Russia. У меня один вопрос по поводу первого метода. Получается, вы находите вихри в интерферограмме, так? Ведь, то есть интерферограмма, строго говоря, это нули уже ушли, то есть точки сингулярности, вот эти вихри, они в интерферограмме, то есть отсутствуют, они ушли в другое место. То есть интерфер...
Ну, как
мы...
Ингредиент этого находит во втором методе, когда датчик Гарфмана использует. А в первом методе он по расщеплению линиям этой интерферограммы. Можно показать это слайд? Да, попросите показать.
Покажите, пожалуйста, слайд первого метода.
Ну, где-то впереди там интерферограммы были. В самом
начале.
Еще. Ну вот, пошли. Нет. Ближе к началу где-то должно быть. Еще ближе к началу. Еще. Вот. Так, ну вот интерферограммы. Да, мы тут не видим минимумов, но... И это, кстати, экспериментальные результаты. Ну вот, если... Ну, как вы сказали, нули ушли. Да, я с вами соглашусь, ушли. Но это только первый и второй порядок. Нулей нет. А вот если мы возьмем интерферограммы более высоких порядков, там появляются нули, и там дополнительные сложности с определением положения вихря. То есть вот для низших порядков, да, здесь нет нулей, но вихрь-то находится без проблем. А вот для более высоких порядков там сложности.
То есть у вас, вот, допустим, вот одна, ну тут, точнее, две вилочки вот такие вот. То есть вы потом их дальше обрабатываете, ну, то есть фазу?
В своей программе считываем и обрабатываем.
Ясно. Просто вопрос был в том, что если вот по сути поле интерферограммы, ну, сингулярности в нем не идентичны полю тому, что изначального вихря, ну, пучка с вихрем, который был. Вот. То есть, когда мы складываем, получается, они могут уйти. Ладно. Ну, я, кажется, понял. Спасибо.
Ну, то есть, в интерферограммах для дислокации низших порядков мы действительно нули не видим. Это в численном эксперименте и в реальном. А вот в интерферограммах для вихрей более высоких порядков там вполне может возникнуть черное пятно.
Я так понимаю, еще здесь, ну, суть вопроса еще в том заключалась, что опорная волна, она может содержать какие-то искривления волнового фронта, которые влияют на...
Ну, она даже без искривлений, ну, если посмотреть факты...
Без искривлений бы справиться.
Ну, я имею в виду, что вот чисто в эксперименте, если когда вы работаете, то волновой фронт, ну, предполагается, что у вас волна плоская, но на практике она может содержать какие-то дефекты, которые тоже внесут дополнительные искажения.
А вот дефекты будут проявляться в том, что линии будут не прямо вот сверху вниз проведены в интерференционной картине, а вот немного вот так вот загибаться в какую-либо сторону. Но это в простейшем случае. А более сложные искажения, ну, я не знаю уж, они всяко могут идти.
Ну, ясно. Хорошо. Я думаю, что мы должны переключаться на стендовую сессию. Вот еще один комментарий, пожалуйста. К микрофону.
Если я не ошибаюсь, в эксперименте, когда у нас волновые фронты совмещены, то мы вилочку получим, да? А если у нас при интерференции волновые фронты будут немножко наклонены друг к другу, то вот эта вилочка, она будет спираль вырождаться. Это так ведь?
Ну вот я не пробовал. Что... Нет, так как они же все равно будут наклонены волновые фронты друг к другу.
Вы попробуйте под наклоном их посмотреть интерференцию, когда опорная волна немножко под углом падает. Вот если не ошибаюсь, там все-таки спираль будет. Вот. Поэтому...
У меня не получались спирали.
Можно добавить. Спираль
когда соосно?
В случае, когда соосно, но расходимость разная, тогда идет спираль. А если волновые фронты выровнены, тогда вилочка.
Ну вот у меня в эксперименте, который не я делал.
Нет, подождите. Если соосно, то это означает, что волновые фронты, они выровнены и так. Вот как бы. Вы же противоречие возникает.
Нет. Если у вас идет два пучка, вы в интерферометре направление ставите разное, но просто вставляете линзу, которая дает пучку расходимость. Допустим, у вас...
Ну, про линзу-то да, понятно. Ладно, спасибо.
Спасибо большое еще раз за доклад. Я хотел бы закрыть нашу сегодняшнюю интернет-сессию. Я считаю, что за исключением небольших технических трудностей все прошло успешно. Спасибо всем принявшим участие, в первую очередь докладчиков и во вторую, конечно, своей аудитории. Спасибо. Увидимся завтра. А сейчас у нас стендовая сессия. Yes. I would like to duplicate my message in English. Now we have time to close the second day of our internet sessions, and now we are approaching to the poster session. It will be on site, unfortunately not in online, but tomorrow I think we will have translation of our conference again, and thank you for everyone for our brilliant talks and speakers, and thank for the all who have listened these talks. Thank you.